Boiling thousands of gallons of fresh milk down to thick and sweet perfection is a factory process powered by incredible technology. What starts as raw dairy is rapidly transformed into one of the richest and most shelf-stable ingredients in the world. In this documentary, we take you inside the industrial world of condensed milk production, where giant machines evaporate and can this creamy staple at a massive scale. The industrial production of condensed milk begins with the careful reception and preparation of raw cow's milk, a phase that determines the quality, efficiency, and final yield of the entire operation. As raw milk arrives at the condensed milk manufacturing facility, typically transported in insulated stainless steel tankers from contracted dairy farms, the first priority is immediate and rigorous quality assessment. Each truckload contains tens of thousands of liters of milk, and every batch must be verified to meet precise industrial standards before being accepted into the plant's supply chain. This initial phase involves a set of standardized protocols carried out in a dedicated receiving bay, equipped with specialized sampling and testing equipment. Upon arrival, the truck is docked to an unloading station, where automated lines connect directly to the tanker's valve. Before unloading can commence, operators perform a series of tests on a representative sample extracted from the tanker. This is done using a sanitized dipper or through a sample port using aseptic techniques to avoid contamination. The sample is then transferred to the plant's on-site quality control lab. Inside this lab, technicians first conduct a sensory inspection, evaluating the milk's color, smell, and presence of any visible particulates. While this step is basic, it's essential in immediately identifying any batches with gross spoilage or foreign contamination. The next series of tests are chemical and microbiological. A cryoscope is used to determine the freezing point of the milk, which helps identify dilution with water. Industrial condensed milk relies on unadulterated raw milk with tightly controlled fat and solids not fat contents. Any dilution affects the solids concentration required for the evaporation phase later on. Following this, infrared spectroscopy or mid-infrared analyzers are used to determine precise fat, protein, and lactose levels. These readings are compared against production targets, usually 3.5 to 4.0% fat and 8.5 to 9.0% SNF. If any component falls out of range, the milk may be either rejected or diverted to other dairy product lines. Another critical check is for microbial load. A rapid plate count, or ATP bioluminescence test, evaluates the total bacterial count per milliliter. Condensed milk production cannot start with high bacterial loads, as the concentration process would also concentrate any microbial byproducts, leading to off flavors and safety risks. Acceptable raw milk generally must have fewer than 100,000 colony-forming units per ml, with many plants enforcing even tighter limits. Additionally, presence of pathogens such as Listeria or Salmonella are monitored using immunoassay kits or PCR-based rapid tests. Antibiotic residue testing is also performed using either SNAP tests or microbial inhibition assays, since antibiotic contamination can disrupt the fermentation steps used in other dairy operations and might violate export regulations. If the sample passes all tests, the milk is cleared for unloading. The truck's contents are then pumped via sanitary stainless steel pipelines into raw milk holding tanks located within a temperature-controlled section of the facility. These tanks, typically ranging from 20,000 to 50,000 liters in capacity, are jacketed and agitated to maintain a constant temperature of around 4 degrees Celsius. At this stage, the milk is still unpasteurized and considered perishable, so time and temperature control are critical. The tanks are equipped with inline thermometers and CIP spray balls that will sanitize the internal surfaces between batches to prevent cross-contamination. The next step in the process is milk clarification and standardization. This is a pivotal moment where physical impurities and excess variability in composition are removed. The raw milk is fed from the storage tanks to a centrifugal clarifier, a high-speed rotating bowl separator that uses the density differences between milk solids and liquid to remove somatic cells, dirt, and other non-milk particles. The milk enters the spinning drum through a feed pipe, and under centrifugal force, heavier particles are flung outward against the bowl walls and discharged intermittently via sludge ejection ports. After clarification, the milk is sent to a cream separator. This piece of equipment operates similarly to the clarifier, but focuses on removing and isolating the cream layer from the skim milk portion. Depending on the desired end product specifications, some or all of the separated cream may be blended back in. This is where the standardization process comes into play. Condensed milk requires a tightly defined balance between fat content and total milk solids. Operators adjust this balance using inline blending systems, automated control loops equipped with flow meters and density sensors. The goal is to create a uniform milk base, typically around 8.5% fat and 22% total solids before it proceeds to pasteurization and evaporation. Any deviation at this stage would affect the efficiency of the next stages and could compromise the desired thickness, sweetness, and shelf life of the condensed milk. In more advanced factories, these composition adjustments are performed entirely by automated PLC systems. These use real-time data collected from inline sensors to control proportioning valves and regulate the mixing of cream and skim milk streams without any manual input. This level of automation not only ensures consistency, but reduces waste and energy use. The standardized milk is now homogeneous in composition, free of debris, and ready for thermal treatment. Before entering the pasteurizer, it may pass through a deaerator, a vacuum chamber that removes entrapped gases such as oxygen and carbon dioxide, which, if left in, could promote oxidation of fats and off flavors during storage. But up next is a step that changes the physical properties of the milk at a fundamental level. With the raw milk now cleaned, standardized, and compositionally balanced, it's time for it to undergo pasteurization and heat treatment, a step that prepares it for concentration without microbial risk or protein denaturation. This phase involves an intricate dance between temperature, pressure, and time, and it sets the stage for the transformative evaporation process that gives condensed milk its name. Now that the raw milk has been thoroughly received, clarified, and compositionally standardized, it is ready for thermal treatment. The next phase in the factory process is pasteurization, which is critical in destroying any pathogenic or spoilage microorganisms present in the milk. Pasteurization must be done with precise timing and temperature control to ensure microbial inactivation without damaging the milk's nutritional or functional properties, especially since this milk will soon undergo evaporation, which puts it under further thermal stress. To carry this out, the milk is directed from the holding tanks into a continuous flow, high-temperature, short-time pasteurization unit, which is the standard in industrial dairy processing. The HTST system typically consists of a series of plate heat exchangers that are engineered to raise the milk temperature to approximately 85 degrees Celsius for 15 to 20 seconds. This is hotter and slightly longer than conventional drinking milk pasteurization, as condensed milk requires greater microbial stability due to its extended shelf life. The process begins in the regeneration section of the plate heat exchanger, where incoming cold raw milk is preheated by outgoing pasteurized milk, allowing energy recovery and efficiency gains of up to 90%. The milk then moves through the heating section, where it is brought to the target temperature using hot water or steam circulated on the opposite side of the stainless steel plates. The timing of exposure is controlled by the flow rate and volume of the holding tubes. ensuring that every particle of milk receives uniform treatment. After pasteurization, the milk passes into a holding cell monitored by thermocouples and flow diversion valves. If the milk fails to reach or maintain the required pasteurization conditions, it is automatically diverted back to the raw milk tank for reprocessing. Once verified, the pasteurized milk is cooled again in the regeneration section, where it gives off its heat to the incoming raw milk, and then further chilled to around 60 degrees Celsius in preparation for the next crucial step, evaporation. Before entering the evaporator, the milk passes through a balance tank that helps maintain a constant feed rate into the evaporation system, stabilizing flow and avoiding temperature fluctuations that could cause burn-on or fouling inside the evaporator tubes. Now it's time to go into the evaporation stage, which is arguably the heart of the condensed milk production process. This is where the milk is physically transformed, thickened into a rich, viscous product through the removal of water. The goal here is to reduce the water content from its original 87% down to around 60%, achieving a final concentration of about 28% milk solids and 44% added sugar in the case of sweetened condensed milk. This is achieved through multi-effect vacuum evaporation, an energy-efficient process that allows for large-scale water removal without subjecting the milk to damaging high temperatures. The milk enters a multiple-effect falling film evaporator, which is the industry standard for large volume dairy processing. In this system, the pasteurized milk is introduced at the top of vertical stainless steel tubes where it forms a thin film as it flows downward. Simultaneously, steam is injected into adjacent chambers that surround the tubes, heating them indirectly. Because the evaporator is operated under vacuum, often at pressures around 70 to 100 millibar, the boiling point of the milk is reduced to around 55 degrees Celsius. This protects the sensitive proteins, sugars, and fats from heat-induced damage, preserving both flavor and nutritional quality. In a multi-effect setup, the vapor produced from one stage is used to heat the next stage, drastically improving energy efficiency. A typical 5-effect evaporator can remove over 85% of the water from milk with minimal energy input, thanks to this cascading reuse of thermal energy. The evaporated water is condensed and collected as waste heat condensate, which can later be recycled within the plant for cleaning processes or steam generation. Inside the evaporator, the thin film of milk continuously loses moisture as it falls. The combination of short residence time, low boiling point, and efficient heat transfer ensures that concentration occurs evenly and rapidly. By the time the milk reaches the bottom of the final effect, it has reached a viscous, concentrated state with a solid content of around 45%. At this point, it is discharged into an intermediate concentrate tank, where it is gently agitated and kept warm to prevent crystallization or skin formation on the surface. But the evaporation process alone does not fully define condensed milk as we know it, especially in the case of sweetened condensed milk. Once the desired solids concentration is achieved, the next critical step is the addition of sugar, which is not merely for taste, but serves as a functional preservative. The high sugar content lowers the water activity of the product to a point where microbial growth is virtually halted, granting it a long shelf life without refrigeration. The method of sugar addition must be extremely precise, as the wrong concentration can lead to issues like crystallization, viscosity problems, or even fermentation in rare cases. To do this, refined white sugar, typically sucrose, is added to the concentrated milk in the form of a hot sugar syrup. This syrup is prepared separately in jacketed mixing vessels, where dry granulated sugar is dissolved in water and heated to around 70 degrees Celsius. The syrup is filtered to remove any particulate matter and pumped into the concentrate tank under controlled flow rates. The typical formulation is around 44. 46% sucrose by weight in the final product, which is determined by a combination of inline refractometers and density meters. The mixing of sugar syrup into the concentrate must be uniform to prevent localized crystallization and is often aided by low shear agitators that maintain homogeneity without introducing air. As the sugar is added, the milk becomes even more viscous and dense. At this point, the product's temperature is carefully maintained between 60 degrees Celsius and 65 degrees Celsius, as dropping below this range can initiate premature crystallization, while higher temperatures can scorch the milk solids. Once the sugar is fully integrated, the mixture is briefly held in a jacketed holding tank for a process known as equilibration, which allows any remaining air bubbles to rise and dissipate and gives time for the solution to reach equilibrium in terms of water activity and solute concentration. This marks the end of the thermal and compositional transformation stages. From a microbiological and physicochemical standpoint, the product is now shelf-stable, viscous, and chemically preserved by both heat treatment and high sugar concentration. However, it's not yet ready for packaging. There are still important steps to take involving cooling, crystallization control, and downstream finishing that are vital to achieving the smooth texture and glossy appearance that define high-quality condensed milk. With the concentrated sweetened milk now fully blended and equilibrated, the next critical phase in the condensed milk manufacturing process is controlled cooling and crystallization. This step is vital not only to achieving the desired texture and viscosity, but also to ensuring long-term product stability. If cooling is done too quickly or without proper control over nucleation, the lactose and sucrose in the product can crystallize into large, gritty particles. This not only affects mouthfeel, but can also lead to phase separation over time. To avoid this, the condensed milk is sent through a carefully engineered cooling and seeding system that promotes the formation of microcrystals, small, evenly distributed sugar crystals that give condensed milk its signature smooth, glossy consistency. The cooling system typically consists of scraped surface heat exchangers or jacketed tubular coolers. These systems are designed to handle highly viscous liquids and provide a high degree of thermal control. In scraped surface heat exchangers, the condensed milk flows through a cylindrical barrel while rotating blades constantly scrape the inner surface. This ensures that no product burns or sticks to the hot surface, and that the entire volume of milk is uniformly cooled. The cooling medium, usually chilled glycol or water, is circulated through the jacket, gradually lowering the milk temperature from around 65 degrees Celsius to 30-35 degrees Celsius. As the milk cools, it passes through a crystallization chamber where it is inoculated with fine lactose or sucrose seed crystals. These seed crystals are introduced in a controlled manner using a dosing system that meters out microscopic crystals with a high surface area. The goal is to initiate crystallization at a molecular level, encouraging the dissolved sugars to form consistent and extremely fine crystals rather than large, coarse ones. Agitators in the crystallization chamber are designed to promote gentle but thorough mixing, ensuring uniform distribution of the seed material without incorporating excess air, which could lead to oxidation or microbial contamination. Once seeded, the mixture is held at a stable crystallization temperature, typically around 30 degrees Celsius, for a period ranging from 30 to 90 minutes, depending on the batch size and product formulation. This resting period allows the crystals to grow slightly while remaining small and suspended, forming a delicate lattice within the viscous matrix of the milk. It is during this stage that the final texture of the condensed milk is locked in. Operators closely monitor the product's Brix value, viscosity, and temperature, using inline sensors and laboratory sampling to ensure that the crystallization proceeds according to specification. After the crystallization phase, the product enters the Deaeration stage. Despite all precautions taken Condensed milk will inevitably contain some entrapped air, either from mechanical mixing, seeding, or agitation. This air must be removed before packaging to prevent oxidation, which can degrade both flavor and color over time. Deaeration also helps improve fill accuracy during packaging, ensuring a stable and uniform product weight in each container. Deaeration is typically carried out in a vacuum deaerator tank. The condensed milk is pumped into the tank, which is maintained under a vacuum of around -0.8 bars. Inside the tank, the milk is spread into a thin film across a series of rotating trays or falling film surfaces, maximizing the exposed surface area. As the product spreads out under vacuum, dissolved gases and trapped air are released and drawn out by the vacuum pump system. In some systems, nitrogen gas is also bubbled through the product as a stripping agent to help displace oxygen more effectively. This process is continuously monitored with oxygen sensors to ensure minimal residual oxygen levels in the final product, typically less than 0.5 milligrams per liter. Once deaerated, the condensed milk is often passed through a final homogenization stage. While not strictly required in all formulations, homogenization is frequently used to improve product consistency, prevent fat separation, and extend shelf stability. In this process, the milk is forced through a narrow orifice under high pressure, usually between 100 to 150 bar, causing the fat globules to break down into much smaller sizes, typically less than 1 micron in diameter. This prevents creaming or separation during storage and gives the final product a more uniform mouthfeel. The homogenizer used in this step is typically a two-stage piston-type homogenizer. In the first stage, pressure is applied to break apart the fat globules. In the second stage, the product is passed through an impact ring to further disperse and stabilize the emulsion. This ensures that the fat remains evenly distributed throughout the viscous condensed milk matrix, even after months of storage on a shelf. The process must be carefully balanced to avoid over-shearing the product, which could break the sugar crystal structure and lead to syneresis or texture issues. With the product now fully processed, it moves to the packaging line. Before any milk enters a can or a tube, the packaging material itself must undergo preparation. Metal cans are the most common format for condensed milk, though plastic tubes and laminated pouches are also used depending on market demands. The cans arrive at the factory either as pre-formed containers or as rolled flat blanks that are formed and sealed on site using can-forming machinery. If using pre-formed cans, the first step is depalletizing and feeding. The cans are automatically unloaded from shipping pallets and fed into a cleaning system via conveyor belts. Here, they pass through a high-pressure air blower system that removes dust and debris. They may also pass through an inverted rinse tunnel that sprays them with sterile water or a mild sanitizing solution. Optical sensors verify that each can is intact and free of damage before it proceeds. The clean cans are then transported to the filling station, where they are indexed into position beneath nozzles connected to a positive displacement filler system. These filling machines are designed to handle thick, viscous liquids with high precision. A typical condensed milk filling machine includes a volumetric dosing mechanism that ensures every can receives the exact same quantity, usually around 397 grams, the standard retail size. Sensors ensure the nozzles do not drip or splash, and the filling process is conducted in a low oxygen environment to prevent post-process contamination. As cans are filled, they immediately move to the vacuum closing station. This is another critical step in ensuring product longevity. Before the lid is sealed, a vacuum is applied to the headspace in the can to remove residual air. This helps prevent oxidation and maintains the slight negative pressure required for a tight seal. The lid is then applied and hermetically sealed using a double seam seaming machine. This creates an airtight seal by mechanically folding and compressing the lid and can flange together in 2 operations. The quality of this seal is checked automatically using seam gauges and vision inspection systems to detect any defects or incomplete closures. After sealing, the cans enter a hot water bath or steam chamber for thermal holding. This step, known as in-can sterilization or thermal stabilization, involves heating the sealed cans to around 85 to 90 degrees Celsius for 15 to 20 minutes. This serves several functions. It neutralizes any residual microbes that may have entered during filling, helps equalize pressure inside the can, and further reduces the water activity of the product. The heating process is tightly controlled using a time temperature data logger to ensure consistency across batches. Once the thermal holding is complete, the cans are rapidly cooled using chilled water sprays or immersion tunnels. This quick cooling halts the cooking process and helps set the product structure inside the can. It also prevents over-darkening, which can occur due to Maillard reactions between milk proteins and sugars at elevated temperatures. The cans are then dried using air knives and conveyed to the labeling and coding area. Each can is now labeled with full product information, including nutritional facts, production batch codes, expiration dates, and allergen warnings. Laser coders or inkjet printers apply traceability codes directly onto the lid or bottom of each can, allowing for full tracking throughout the supply chain. These codes are critical for food safety as they allow for rapid recall or identification of affected batches in the rare event of a contamination issue. From here, the cans are packed into cartons or shrink-wrapped into bundles using automated case packers. The cartons are stacked onto pallets and wrapped with stretch film for transport. At this stage, finished condensed milk is subjected to final quality inspection, where random samples from each batch are tested for Brix value, fat content, microbial load, viscosity, and packaging integrity. Once the batch is cleared, it is released for distribution. With the cans now fully sealed, labeled, and palletized, the condensed milk moves into the final stretch of its industrial journey: post-production storage, distribution, and market readiness. While it may seem that the heavy lifting is over, these concluding steps are far more complex and technologically managed than they first appear. Factories invest significant resources to ensure that every can of condensed milk not only leaves the facility in perfect condition, but also maintains its quality throughout the entire shelf life, often up to 2 years or more. Immediately after packaging, pallets of condensed milk are transferred to temperature-controlled finished goods warehouses. The climate in these storage areas is tightly regulated, typically kept between 15 degrees Celsius and 25 degrees Celsius, with relative humidity under 60%. This environment prevents moisture accumulation on the can surfaces and limits the rate of any chemical reactions inside the product, such as non-enzymatic browning. Even though the condensed milk is shelf-stable, excessive heat over time can darken the color and subtly change the flavor profile. These storage conditions are monitored 24/7 using IoT-connected environmental sensors that send real-time data to the facility's central control system. Each pallet is barcoded with batch numbers and entered into a digital warehouse management system. This system not only tracks location and inventory levels, but also enforces FIFO protocols to ensure older batches are distributed before newer ones. The traceability codes printed earlier on the cans come into play again here. Every single unit can be traced back to its raw milk intake, processing parameters, operator ID, and time-stamped process logs. This full chain traceability is a critical part of modern food safety compliance. When orders are received from retailers, exporters, or institutional buyers, automated robotic pallet pickers retrieve the relevant stock and move it to the outbound shipping area. Here, it is loaded into refrigerated or insulated trucks, depending on the destination and regional climatic conditions. In many cases, international shipments involve placing pallets into reefer containers that maintain stable temperatures for transoceanic shipping routes. Standardization is the next critical step in butter production. This involves adjusting the fat content of the cream to a consistent level, usually around 40%, which is optimal for churning into butter. Advanced machinery is employed to blend cream with varying fat contents or to add skim milk as needed. This precise adjustment ensures uniformity in the final product. Standardization also allows factories to produce different types of butter, such as light or extra rich varieties, by altering the fat percentage accordingly. The standardized cream is then pasteurized to eliminate any harmful bacteria and to enhance shelf stability. Pasteurization involves heating the cream to a specific temperature for a set duration, followed by rapid cooling to prevent spoilage. After pasteurization, the cream enters the aging phase. This step is crucial for developing the desired texture and flavor profile of the butter. During aging, the cream is stored at a controlled temperature for several hours, allowing natural enzymes and lactic acid bacteria to work on the fat molecules. For cultured butter production, additional bacterial cultures are introduced during this stage to impart a richer, more complex flavor. The aging process can vary depending on the type of butter being produced, with some recipes requiring longer periods to achieve the desired characteristics. Once the cream has been adequately aged, it moves to the churning stage. In industrial settings, large-scale churns are used to efficiently process vast quantities of cream. The churning process separates the butterfat from the buttermilk through continuous agitation. As the cream is churned, the fat globules begin to coalesce, forming small grains of butter. These grains gradually grow larger as the churning continues, eventually forming a cohesive mass of butter. The buttermilk, which is the liquid component remaining after the fat solids have separated, is drained off and often used in other food products, such as baking ingredients or animal feed. Following churning, the butter mass undergoes washing to remove any residual buttermilk and impurities. Cold water is carefully sprayed over the butter while it is continuously agitated to ensure thorough cleaning. This step is vital for improving the texture and extending the shelf life of the butter. After washing, the butter is worked to achieve the desired consistency. If salted butter is being produced, salt is added at this stage to act as a preservative and enhance flavor. The amount of salt varies based on the specific product requirements and regional preferences. The working process involves kneading the butter to distribute the salt evenly and to expel any remaining water. The packaging phase is the next significant step in butter production. At this point, the butter is shaped into blocks, tubs, or sticks, depending on the intended market. Modern factories utilize automated equipment to shape and package the butter efficiently. Each piece is weighed precisely to ensure accurate portioning. Packaging materials are selected for their ability to protect the butter from environmental factors such as light, air, and moisture, which can degrade its quality. Common packaging options include foil-wrapped blocks, plastic tubs, and stick wrappers. The design of the packaging often incorporates branding elements and nutritional information to appeal to consumers. Throughout the entire production process, quality control measures are rigorously enforced to maintain the integrity of the butter. Multiple checks and tests are conducted at various stages to ensure compliance with safety and quality standards. Microbiological testing confirms the absence of harmful bacteria, while physical tests assess the texture and spreadability of the butter. Chemical analysis verifies the fat content and flavor profiles. Sensory evaluation panels may also assess the taste, aroma, and appearance of the butter to ensure it meets consumer expectations. Any batch that fails to meet these criteria is either reprocessed or discarded to uphold product quality. Factories implementing sustainable practices aim to minimize their environmental impact. Waste materials, such as the buttermilk separated during churning, can be further processed to create valuable byproducts like whey protein. Energy usage is optimized through the recovery of waste heat generated during thermal processes. such as pasteurization, which can be reused within the factory. Water used in washing and cleaning operations is treated before discharge to comply with environmental regulations. These efforts contribute to a more sustainable and eco-friendly production process. Technological advancements have significantly enhanced the efficiency and precision of butter production in factories. Computer-controlled systems monitor and adjust parameters such as temperature, speed, and timing during each stage of the process. Robotics and artificial intelligence are increasingly integrated into factory operations to improve accuracy and reduce human error. For example, automated sensors can detect inconsistencies in the cream's fat content during standardization and make real-time adjustments to correct them. These innovations not only streamline the production process, but also allow for greater customization and flexibility in meeting diverse market demands. Consumer trends play a pivotal role in shaping butter production strategies. With growing interest in health-conscious eating, there is an increasing demand for low-fat or plant-based alternatives. Factories respond by developing new recipes and production methods to cater to these emerging preferences. Transparency in sourcing and production practices is becoming increasingly important to consumers, leading factories to adopt traceability systems that provide detailed information about the origin and journey of their products. This builds trust and enhances brand loyalty among customers. The global market for butter is influenced by a variety of factors, including dietary habits, cultural preferences, and economic conditions. Factories must remain adaptable and responsive to these changes to stay competitive. They invest in research and development to innovate and improve their products continuously. Collaboration with suppliers, retailers, and consumers helps factories understand market needs and align their production strategies accordingly. By leveraging technology, adhering to quality standards, and embracing sustainable practices, butter factories aim to deliver superior products that meet and exceed customer expectations. In the context of industrial butter production, the procurement of raw cream is a meticulous process. Cream is sourced from dairy farms that adhere to stringent quality protocols. Upon arrival at the factory, the cream is tested for fat content, microbial levels, and overall purity. Approved cream is stored in refrigerated tanks at a precise temperature to maintain freshness. Standardization adjusts the fat content to approximately 40%, using advanced machinery to blend cream with varying fat contents or add skim milk as necessary. This step ensures uniformity in the final product and enables the production of different butter varieties by altering the fat percentage. Pasteurization follows standardization, involving heating the cream to a specific temperature for a set duration to eliminate harmful bacteria and enhance shelf stability. After pasteurization, the cream enters the aging phase, where it is stored at a controlled temperature for several hours to develop the desired texture and flavor. Cultured butter production introduces additional bacterial cultures during this stage to impart a richer flavor. Churning separates the butter fat from the buttermilk through continuous agitation, forming small grains of butter that grow larger as the process continues. The buttermilk is drained off and often utilized in other food products. Washing removes residual buttermilk and impurities from the butter mass using cold water while it is continuously agitated. Salt is added during the working process if producing salted butter, enhancing flavor and acting as a preservative. Automated equipment shapes and packages the butter into blocks, tubs, or sticks with precise weighing, ensuring accurate portioning. Packaging materials protect the butter from environmental factors, incorporating branding elements and nutritional information to appeal to consumers. Quality control measures are enforced throughout the production process, with multiple checks and tests ensuring compliance with safety and quality standards. Microbiological testing confirms the absence of harmful bacteria. Physical tests assess texture and spreadability, and chemical analysis verifies fat content and flavor profiles. Sensory evaluation panels assess taste, aroma, and appearance to meet consumer expectations. Sustainable practices minimize environmental impact, recycling waste materials, optimizing energy usage, and treating water before discharge. Technological advancements enhance efficiency and precision with computer-controlled systems, monitoring and adjusting parameters during production. Consumer trends shape production strategies, driving innovation in recipes and methods to meet health-conscious demands and build transparency through traceability systems. Collaboration with stakeholders helps factories understand market needs and align production strategies accordingly, delivering superior products that exceed customer expectations. Industrial butter production involves intricate steps and considerations, balancing tradition with innovation. From cream preparation to final packaging, every stage is meticulously controlled to ensure high-quality butter. Advanced technologies, adherence to quality standards, and sustainability initiatives enhance efficiency and reduce environmental impact. Adapting to consumer trends ensures relevance in a competitive market, demonstrating the industry's commitment to responsible and forward-thinking practices. Butter production in factories combines art and science, transforming simple cream into a beloved staple enjoyed worldwide. The journey of butter from cream to table showcases the complexity and sophistication involved in industrial-scale production. Precise control over every stage, rigorous quality assurance, and integration of modern technologies highlight the dedication to delivering a versatile and delicious product. This exploration reveals the detailed processes and considerations that define butter production in a factory setting. Cream acquisition begins with sourcing from dairy farms, adhering to quality protocols. Testing ensures fat content, microbial levels, and purity meet standards. Approved cream is stored in refrigerated tanks at controlled temperatures. Standardization adjusts fat content to 40% using advanced machinery, enabling uniformity and variety production. Pasteurization eliminates bacteria and enhances shelf stability through precise heating and cooling. Aging develops texture and flavor, with cultured butter benefiting from additional bacterial cultures. Churning separates butterfat from buttermilk, forming grains that grow larger during continuous agitation. Buttermilk is drained off for reuse in other food products. Washing removes impurities using cold water while agitating the butter mass. Salt is added during the working process for flavor enhancement and preservation. Automated equipment shapes and packages butter into blocks, tubs, or sticks, with precise weighing ensuring accurate portions. Packaging materials protect against environmental factors, incorporating branding and nutritional information. Quality control enforces safety and quality standards through microbiological testing, physical assessments, and chemical analyses. Sensory evaluations ensure taste, aroma, and appearance meet expectations. Sustainable practices minimize environmental impact by recycling waste, optimizing energy use, and treating water before discharge. Technological advancements enhance efficiency and precision, with computer-controlled systems monitoring production parameters. Consumer trends drive innovation in recipes and methods, promoting health-conscious alternatives and transparency through traceability systems. Collaboration with stakeholders aligns production strategies with market needs, delivering superior products exceeding customer expectations. The creation of mayonnaise in a factory is an intricate process that combines the precision of science with the artistry of culinary expertise. At its essence, mayonnaise is an emulsion, a delicate blend of oil, water, and egg yolks stabilized by natural emulsifiers such as lecithin. This journey from raw ingredients to jarred condiment involves numerous steps, each meticulously controlled to ensure consistency, flavor, and safety. It all begins with the procurement of high-quality raw materials. Eggs, vegetable oil, vinegar, and various seasonings form the foundation of mayonnaise production. Eggs, particularly their yolks, are crucial because they contain lecithin, a natural emulsifier that binds oil and water together. These eggs must meet stringent standards for freshness and cleanliness before entering the facility. Similarly, the choice of oil is critical. It must be pure and flavorful, as it significantly influences the taste of the final product. Vinegar serves dual purposes, acting as both a preservative and a flavor enhancer. Additional seasonings like salt, sugar, mustard powder, or garlic extract may also be added depending on the desired variety. Once these ingredients arrive at the factory, they undergo rigorous testing to ensure compliance with quality specifications. Microbial contamination, pH levels, and chemical composition are carefully checked. Approved ingredients are then stored in large tanks or silos under controlled conditions to preserve their integrity until needed. Eggs are often pasteurized at this stage to eliminate any potential pathogens, ensuring the safety of the final product. The heart of mayonnaise production lies in the mixing process, where individual components are transformed into a smooth, creamy emulsion. Initially, egg yolks are blended with vinegar and seasonings in a specialized mixer. This mixture acts as the base, providing the foundation for the emulsion. As the blending continues, liquid vegetable oil is slowly introduced into the mix. The key here is gradual addition. Pouring the oil too quickly can destabilize the emulsion, leading to separation. Advanced machinery, equipped with precise flow control mechanisms, ensures that the oil is incorporated at just the right rate, maintaining stability throughout the process. During this phase, the mechanical action of the mixer helps break down the oil into microscopic droplets, dispersing them evenly within the aqueous phase. Lecithin present in the egg yolks plays a pivotal role here, acting as a bridge between the oil and water molecules to prevent them from separating. This step requires careful monitoring of temperature and speed to achieve optimal results. Too much heat can denature the proteins in the egg yolks, compromising the emulsion, while insufficient agitation might leave the mixture lumpy or inconsistent. Once the initial emulsion has been formed, further adjustments may be made to fine-tune the texture and flavor. Additional ingredients, such as stabilizers or thickeners, may be added to enhance the viscosity of the mayonnaise, ensuring it maintains its creamy consistency over time. Some manufacturers also incorporate antioxidants to extend shelf life and preserve freshness. These additions are done using automated systems that measure quantities with remarkable accuracy, guaranteeing uniformity across batches. After the mixing process is complete, the mayonnaise moves to the homogenization stage. Homogenization involves subjecting the mixture to intense pressure through narrow channels, breaking down any remaining large oil droplets into even smaller particles. This step not only improves the stability of the emulsion, but also enhances the smoothness and silkiness of the final product. Modern factories use sophisticated homogenizers capable of processing vast quantities of mayonnaise efficiently while maintaining consistent quality. Next comes the pasteurization phase, a critical step in ensuring the safety of the mayonnaise. Although the eggs have already been pasteurized earlier in the process, the entire mixture is heated to a specific temperature for a set period to eliminate any residual bacteria or microorganisms. Pasteurization also helps stabilize the flavors, allowing them to meld together harmoniously. After heating, the mayonnaise is rapidly cooled to prevent degradation of its texture or nutritional value. With the mayonnaise now fully prepared, it proceeds to the packaging stage. Here, advanced filling machines dispense precise amounts of the product into jars, bottles, or sachets, depending on the intended market. Packaging materials are chosen for their ability to protect the mayonnaise from light, air, and moisture, which could otherwise compromise its quality. For instance, opaque plastic containers or glass jars with tight-fitting lids are commonly used to shield the contents from external factors. Each package is sealed hermetically to ensure freshness until it reaches the consumer. Quality assurance is woven seamlessly into every aspect of mayonnaise production. Throughout the process, samples are regularly taken and analyzed to verify that the product meets all required standards. Microbiological tests confirm the absence of harmful bacteria, while sensory evaluations assess factors such as color, aroma, and taste. Physical properties such as viscosity and spreadability are also measured to ensure the mayonnaise performs well when used in culinary applications. Any deviations from established norms trigger immediate corrective actions, ensuring that only the highest quality mayonnaise leaves the factory. In addition to producing standard mayonnaise, many factories specialize in creating variations tailored to specific tastes and dietary preferences. Reduced fat versions substitute some of the oil with water or other ingredients to lower calorie content without sacrificing flavor. Low sodium options cater to health-conscious consumers, while organic or vegan alternatives appeal to those seeking more sustainable or plant-based choices. These specialty products require unique formulations and production techniques, showcasing the adaptability of modern manufacturing facilities. Sustainability plays a significant role in contemporary mayonnaise production. Factories increasingly focus on minimizing waste, conserving energy, and reducing environmental impact. Waste oils generated during production are recycled into biofuels or other useful byproducts, while water used in cleaning processes is treated before discharge to comply with ecological regulations. Energy-efficient equipment and renewable energy sources further contribute to greener operations. Moreover, sourcing ingredients responsibly, such as using cage-free eggs or sustainably harvested oils, aligns with growing consumer demand for ethically produced goods. Technological advancements continue to revolutionize the mayonnaise industry. Automation streamlines production lines, enabling faster throughput while maintaining exceptional quality. Artificial intelligence and machine learning algorithms optimize processes by predicting equipment maintenance needs, identifying inefficiencies, and suggesting improvements. Robotics handle repetitive tasks with unmatched precision, freeing human workers to focus on higher value activities. These innovations not only boost productivity, but also allow factories to respond swiftly to changing market demands. Consumer trends heavily influence the evolution of mayonnaise production. With increasing awareness about nutrition and wellness, there is a growing interest in healthier alternatives and transparent labeling. Manufacturers address these concerns by developing innovative recipes and providing detailed information about ingredient origins and production methods. Customization capabilities enable factories to produce niche products catering to regional preferences or emerging dietary fads, such as keto-friendly or gluten-free mayonnaises. Global trade dynamics also shape the way mayonnaise is manufactured. Export markets demand adherence to diverse regulatory frameworks, requiring factories to implement flexible systems capable of meeting varying international standards. Collaboration with suppliers, distributors, and retailers ensures alignment with global supply chains, facilitating timely delivery of products worldwide. Continuous investment in research and development keeps factories at the forefront of technological innovation, ensuring their competitiveness in an ever-evolving marketplace. Beyond the technical aspects of production, the cultural significance of mayonnaise cannot be overlooked. In many regions, it is more than just a condiment. It is a symbol of culinary tradition and innovation. From classic sandwiches to elaborate dressings, mayonnaise serves as a versatile ingredient that enhances countless dishes. Its widespread popularity has driven manufacturers to explore new flavors and textures, expanding its appeal beyond traditional boundaries. For example, flavored varieties infused with herbs, spices, or even fruit extracts offer exciting options for adventurous cooks and diners alike. Factories also prioritize food safety above all else, implementing comprehensive protocols to mitigate risks at every stage of production. Hazard analysis and critical control points. Systems identify potential hazards and establish measures to prevent them. Regular audits and certifications ensure compliance with local and international regulations. Employee training programs emphasize hygiene practices and proper handling procedures, reinforcing a culture of safety throughout the organization. packaging design plays a vital role in the marketing and distribution of mayonnaise. Modern factories invest heavily in developing attractive and functional packaging solutions that appeal to consumers while protecting the product. Innovations in material science have led to the creation of lightweight yet durable containers that reduce shipping costs and environmental impact. Resealable caps and squeezable bottles enhance user convenience, making it easier for customers to enjoy the product without compromising freshness. Supply chain management is another critical component of successful mayonnaise production. Efficient logistics ensure a steady flow of raw materials into the factory and finished goods out to retailers. Strategic partnerships with suppliers help secure reliable sources of high-quality ingredients, while relationships with distributors facilitate rapid delivery to diverse markets. Real-time data analytics enable factories to forecast demand accurately, optimizing inventory levels and reducing waste. Research and development remain central to the growth, and engineers continuously experiment with new formulations, processing techniques, and packaging technologies to improve product quality and sustainability. Emerging trends in biotechnology and fermentation offer promising avenues for enhancing flavor profiles and extending shelf life. Collaborations with academic institutions and research organizations provide valuable insights into cutting-edge developments that can be applied to commercial production. The economic impact of mayonnaise production extends far beyond the factory floor. It supports jobs in agriculture, transportation, retail, and related industries, contributing significantly to local and national economies. By investing in community initiatives and sustainable practices, manufacturers demonstrate their commitment to corporate responsibility and long-term viability. Programs aimed at reducing carbon footprints, conserving water, and promoting biodiversity align with broader societal goals of environmental stewardship. As consumer preferences evolve, so too does the nature of mayonnaise production. Health-conscious individuals seek products with fewer additives and artificial ingredients, driving manufacturers to adopt cleaner label approaches. Clear communication about ingredient sourcing and production methods builds trust and fosters loyalty among discerning customers. Educational campaigns highlighting the benefits of mayonnaise as part of a balanced diet further reinforce its position as a staple in kitchens worldwide. Finally, the future of mayonnaise production promises exciting possibilities. Advances in automation, digitalization, and artificial intelligence will likely transform traditional manufacturing processes, enabling greater efficiency and flexibility. Personalized nutrition platforms may one day allow consumers to customize their own mayonnaise blends based on individual dietary needs and preferences. Meanwhile, ongoing efforts to reduce environmental impact and promote social responsibility will ensure that mayonnaise remains a beloved and sustainable choice for generations to come. Through precise control of every stage, from ingredient preparation to final packaging, factories ensure that each jar of mayonnaise delivers consistent quality and satisfaction. This exploration reveals the depth and complexity behind the seemingly straightforward process of making mayonnaise, highlighting the dedication and expertise required to bring this indispensable condiment to tables everywhere. The production of olive oil in a factory is a meticulous process that combines ancient traditions with modern technology to create one of the world's most revered culinary staples. Olive oil, often referred to as liquid gold, has been cherished for millennia for its rich flavor, health benefits, and versatility in cooking. The journey from olive groves to bottling lines involves several intricate steps, each designed to preserve the natural qualities of the olives while ensuring consistency and quality. It all begins with the cultivation of olives, which are grown primarily in regions with Mediterranean climates such as Spain, Italy, Greece, and parts of North Africa. The choice of olive variety plays a significant role in determining the flavor profile of the final product. Different varieties produce oils with distinct characteristics. Some are fruity and mild, while others are robust and peppery. Harvesting typically occurs between late autumn and early winter when the olives reach their peak ripeness. Timing is crucial because underripe olives yield less oil, while overripe ones can lead to off flavors. Once harvested, the olives are transported to the factory where they undergo rigorous quality checks. These inspections ensure that only healthy, undamaged fruits are used in production. Any leaves, stems, or debris are removed during this stage to prevent contamination. The cleaned olives are then stored temporarily in ventilated containers to maintain freshness until processing begins. The first step in the factory is washing the olives. This process removes dirt, dust, and any remaining impurities from the surface of the fruit. Clean water is sprayed over the olives while they are gently agitated to ensure thorough rinsing. After washing, the olives proceed to the milling stage, where they are crushed into a paste. Traditionally, stone mills were used for this purpose, but modern factories employ stainless steel crushers or hammer mills for greater efficiency. The goal is to break down the cell walls of the olives, releasing the oil trapped inside. Following milling, the olive paste moves to the malaxation phase. Malaxation involves slowly stirring the paste at a controlled temperature to allow small droplets of oil to coalesce into larger ones. This step is critical because it enhances the extraction rate and improves the quality of the oil by promoting better separation of solids and liquids. The duration of malaxation varies depending on factors such as olive variety and desired flavor profile, but it typically lasts between 20 and 40 minutes. After malaxation, the next step is decantation, where the olive paste is separated into its three main components: oil, water, and solid residue known as pomace. In traditional methods, this was achieved using centrifuges or pressing systems. Modern factories predominantly use horizontal decanter centrifuges, which spin the paste at high speeds to separate the heavier solid particles from the lighter liquid phases. The resulting mixture of oil and water is further refined in a second stage centrifuge, which separates the oil completely from any remaining water or fine particles. At this point, the crude olive oil undergoes additional treatments to refine its quality. Filtration is often employed to remove any residual suspended solids, producing a clearer and more stable product. Some manufacturers also implement cold filtration techniques to preserve the natural flavors and aromas of the oil. For extra virgin olive oil, minimal processing is preferred to retain its superior taste and nutritional value. However, lower grade oils may be subjected to chemical refining processes to improve clarity, color, and shelf life. Storage is another critical aspect of olive oil production. Once extracted, the oil is transferred to large stainless steel tanks where it is kept at controlled temperatures to prevent oxidation and degradation. These tanks are equipped with inert gas systems to displace oxygen, further protecting the oil's quality. During storage, the oil continues to settle, allowing any remaining microscopic particles to sink to the bottom of the tank. Periodic sampling and analysis ensure that the oil maintains its desired characteristics throughout this period. Packaging represents the final stage of the production process. Olive oil is bottled in various sizes and formats, ranging from small glass bottles to bulk plastic containers, depending on the target market. Packaging materials are chosen for their ability to shield the oil from light, air, and moisture, which can negatively affect its quality. Dark-colored glass or opaque plastic bottles are commonly used to protect against UV exposure, while tight-fitting caps ensure an airtight seal. Labels provide important information about the oil's origin, grade, and nutritional content, helping consumers make informed purchasing decisions. Quality control is woven into every aspect of olive oil production. Throughout the process, samples are regularly taken and analyzed to verify compliance with strict international standards. Sensory evaluations assess factors such as aroma, taste, and mouthfeel, ensuring the oil meets expectations for its designated grade. Chemical analyses measure parameters like acidity levels, peroxide values, and fatty acid composition to confirm purity and authenticity. Any deviations from established norms trigger immediate corrective actions, guaranteeing that only the highest quality olive oil reaches the market. In addition to producing standard olive oil, many factories specialize in creating premium varieties tailored to specific tastes and dietary preferences. Extra virgin olive oil, considered the finest grade, is produced using mechanical means only, without heat or chemicals, to preserve its natural flavors and antioxidants. Virgin olive oil undergoes slightly more processing, but still retains much of its original character. Refined olive oil, on the other hand, is treated with chemical agents to neutralize defects and achieve uniformity in taste and appearance. Specialty oils infused with herbs, spices, or citrus extracts offer unique flavor profiles that appeal to adventurous cooks and diners alike. Sustainability is increasingly becoming a priority in olive oil production. Factories adopt eco-friendly practices to minimize waste, conserve resources, and reduce environmental impact. Pomace, the solid residue left after extraction, is often recycled into biofuels or animal feed, reducing landfill contributions. Water used in cleaning processes is treated before discharge to comply with ecological regulations. Energy-efficient equipment and renewable energy sources further contribute to greener operations. Moreover, sourcing olives responsibly, such as supporting local farmers who practice sustainable agriculture, aligns with growing consumer demand for ethically produced goods. Technological advancements continue to revolutionize the olive oil industry. Automation streamlines production lines, enabling faster throughput while maintaining exceptional quality. Artificial intelligence and machine learning algorithms optimize processes by predicting equipment maintenance needs, identifying inefficiencies, and suggesting improvements. Robotics handle repetitive tasks with unmatched precision, freeing human workers to focus on higher value activities. These innovations not only boost productivity, but also allow factories to respond swiftly to changing market demands. Consumer trends heavily influence the evolution of olive oil production. With increasing awareness about nutrition and wellness, there is a growing interest in healthier alternatives and transparent labeling. Manufacturers address these concerns by developing innovative formulations and providing detailed information about ingredient origins and production methods. Customization capabilities enable factories to produce niche products catering to regional preferences or emerging dietary fads, such as organic or keto-friendly options. Global trade dynamics also shape the way olive oil is manufactured. Export markets demand adherence to diverse regulatory frameworks, requiring factories to implement flexible systems capable of meeting varying international standards. Collaboration with suppliers, distributors, and retailers ensures alignment with global supply chains, facilitating timely delivery of products worldwide. Continuous investment in research and development keeps factories at the forefront of technological innovation, ensuring their competitiveness in an ever-evolving marketplace. Beyond the technical aspects of production, the cultural significance of olive oil cannot be overlooked. In many regions, it is more than just a cooking ingredient. It is a symbol of heritage and tradition. From drizzling it over fresh bread to using it as the base for elaborate sauces, olive oil serves as a versatile foundation for countless dishes. Its widespread popularity has driven manufacturers to explore new applications and presentations, expanding its appeal beyond traditional boundaries. Factories also prioritize food safety above all else, implementing comprehensive protocols to mitigate risks at every stage of production. Hazard analysis and critical control. Point systems identify potential hazards and establish measures to prevent them. Regular audits and certifications ensure compliance with local and international regulations. Employee training programs emphasize hygiene practices and proper handling procedures, reinforcing a culture of safety throughout the organization. Packaging design plays a vital role in the marketing and distribution of olive oil. Modern factories invest heavily in developing attractive and functional packaging solutions that appeal to consumers while protecting the product. Innovations in material science have led to the creation of lightweight yet durable containers that reduce shipping costs and environmental impact. Resealable caps and pour spouts enhance user convenience, making it easier for customers to enjoy the product without compromising freshness. Supply chain management is another critical component of successful olive oil production. Efficient logistics ensure a steady flow of raw materials into the factory and finished goods out to retailers. Strategic partnerships with suppliers help secure reliable sources of high-quality olives, while relationships with distributors facilitate rapid delivery to diverse markets. Real-time data analytics enable factories to forecast demand accurately, optimizing inventory levels and reducing waste. Research and development remain central to the growth of the olive oil industry. Scientists and engineers continuously experiment with new formulations, processing techniques, and packaging technologies to improve product quality and sustainability. Emerging trends in biotechnology and fermentation offer promising avenues for enhancing flavor profiles and extending shelf life. Collaborations with academic institutions and research organizations provide valuable insights into cutting-edge developments that can be applied to commercial production. The economic impact of olive oil production extends far beyond the factory floor. It supports jobs in agriculture, transportation, retail, and related industries, contributing significantly to local and national economies. By investing in community initiatives and sustainable practices, manufacturers demonstrate their commitment to corporate responsibility and long-term viability. Programs aimed at reducing carbon footprints, conserving water, and promoting biodiversity align with broader societal goals of environmental stewardship. As consumer preferences evolve, so too does the nature of olive oil production. Health-conscious individuals seek products with fewer additives and artificial ingredients, driving manufacturers to adopt cleaner label approaches. Clear communication about ingredient sourcing and production methods builds trust and fosters loyalty among discerning customers. Educational campaigns highlighting the benefits of olive oil as part of a balanced diet further reinforce its position as a staple in kitchens worldwide. Finally, the future of olive oil production promises exciting possibilities. Advances in automation, digitalization, and artificial intelligence will likely transform traditional manufacturing processes, enabling greater efficiency and flexibility. Personalized nutrition platforms may one day allow consumers to customize their own olive oil blends based on individual dietary needs and preferences. Meanwhile, ongoing efforts to reduce environmental impact and promote social responsibility will ensure that olive oil remains a beloved and sustainable choice for generations to come. Through precise control of every stage, from olive cultivation to final packaging, factories ensure that each bottle of olive oil delivers consistent quality and satisfaction. This exploration reveals the depth and complexity behind the seemingly straightforward process of making olive oil, highlighting the dedication and expertise required to bring this indispensable liquid to tables everywhere. The production of whipped cream in a factory is a highly refined process that combines traditional techniques with modern technology to create one of the most beloved and versatile dairy products. Whipped cream, known for its light, airy texture and rich flavor, has become an essential ingredient in desserts, beverages, and culinary creations worldwide. The journey from raw materials to finished product involves several intricate steps, each meticulously controlled to ensure consistency, quality, and safety. It all begins with the procurement of high-quality cream, which serves as the foundation of whipped cream production. Cream is typically sourced from fresh milk, separated through centrifugation or other mechanical processes to concentrate the fat content. For whipped cream, cream with a fat content of around 35% is ideal, as it provides the necessary structure and stability when aerated. The cream must meet stringent quality standards, including checks for purity, fat content, and microbial levels before entering the factory. Once approved, the cream is stored in refrigerated tanks at a precise temperature to preserve its freshness until processing begins. Upon arrival at the factory, the cream undergoes rigorous testing to ensure it meets the required specifications. This includes microbiological testing to confirm the absence of harmful bacteria, chemical analysis to verify fat content, and sensory evaluations to assess flavor and aroma. Approved cream is then standardized to ensure uniformity across batches. Standardization involves adjusting the fat content to the desired level using advanced machinery that blends cream with varying fat contents or adds skim milk as needed. This step is critical for maintaining consistent product quality and enabling customization for different varieties of whipped cream. After standardization, the cream moves to the pasteurization stage. Pasteurization is a crucial step in ensuring the safety and shelf life of the whipped cream. During this process, the cream is heated to a specific temperature for a set duration, followed by rapid cooling. This eliminates any harmful microorganisms while preserving the cream's natural flavors and nutritional properties. Pasteurized cream is then stored at a controlled temperature to maintain its quality until further processing. The next phase in whipped cream production is stabilization. To enhance the cream's ability to hold air and maintain its fluffy texture, stabilizers such as guar gum, carrageenan, or xanthan gum may be added. These ingredients help prevent separation and improve the cream's whipping properties. Emulsifiers like mono and diglycerides may also be incorporated to ensure smooth blending and even distribution of fat globules during aeration. The choice of stabilizers and emulsifiers depends on the desired characteristics of the final product and regulatory requirements in different markets. Once stabilized, the cream proceeds to the whipping stage, where it is transformed into its characteristic light and airy form. In industrial settings, this is achieved using large-scale whipping machines capable of processing vast quantities of cream efficiently. The whipping process involves introducing air into the cream while agitating it at a controlled speed and temperature. As the cream is whipped, the fat globules coalesce, forming a network that traps air bubbles, creating the signature texture of whipped cream. The degree of aeration is carefully monitored to achieve the desired density and volume. During whipping, additional ingredients such as sugar, vanilla extract, or other flavorings may be incorporated to enhance the taste and appeal of the whipped cream. Sugar not only sweetens the product, but also helps stabilize the foam by increasing viscosity and improving bubble formation. Flavorings are carefully selected and measured to ensure they complement the natural richness of the cream without overpowering it. Some manufacturers produce flavored variations, such as chocolate, coffee, or fruit-infused whipped creams, catering to diverse consumer preferences. After whipping, the cream is cooled to stabilize its structure and prevent degradation. Cooling is typically done in a controlled environment to ensure the whipped cream retains its shape and texture. At this stage, the product may undergo further adjustments to fine-tune its consistency and appearance. Advanced machinery is used to measure parameters such as overrun and firmness, ensuring the whipped cream meets the desired specifications. Packaging represents the final stage of whipped cream production. Modern factories utilize automated equipment to dispense precise amounts of the product into various formats, including aerosol cans, plastic tubs, or flexible pouches. Aerosol packaging is particularly popular due to its convenience and ease of use, allowing consumers to spray the whipped cream directly onto their favorite foods. Nitrous oxide is often used as the propellant in aerosol cans, providing both the means of dispensing and contributing to the cream's light texture. Packaging materials are chosen for their ability to protect the whipped cream from light, air, and moisture, which can affect its quality. Labels provide important information about the product's ingredients, nutritional content, and usage instructions, helping consumers make informed choices. Quality control is an integral part of whipped cream production, implemented throughout every stage of the process. Samples are regularly taken and analyzed to verify compliance with strict international standards. Microbiological tests confirm the absence of harmful bacteria, while physical and chemical analyses assess factors such as overrun, firmness, and fat content. Sensory evaluations evaluate the whipped cream's flavor, aroma, and texture to ensure it meets consumer expectations. Any deviations from established norms trigger immediate corrective actions, guaranteeing that only the highest quality whipped cream reaches the market. In addition to producing standard whipped cream, many factories specialize in creating premium varieties tailored to specific tastes and dietary preferences. Low-fat or non-dairy alternatives cater to health-conscious consumers, while organic options appeal to those seeking more sustainable choices. Specialty flavors and textures offer exciting options for adventurous cooks and diners alike. These variations require unique formulations and production techniques, showcasing the adaptability of modern manufacturing facilities. Sustainability plays a significant role in contemporary whipped cream production. Factories increasingly focus on minimizing waste, conserving resources, and reducing environmental impact. Waste cream generated during production is recycled into animal feed or biofuels, while water used in cleaning processes is treated before discharge to comply with ecological regulations. Energy-efficient equipment and renewable energy sources further contribute to greener operations. Moreover, sourcing cream responsibly, such as supporting local farmers who practice sustainable agriculture, aligns with growing consumer demand for ethically produced goods. Technological advancements continue to revolutionize the whipped cream industry. Automation streamlines production lines, enabling faster throughput while maintaining exceptional quality. Artificial intelligence and machine learning algorithms optimize processes by predicting equipment maintenance needs, identifying inefficiencies, and suggesting improvements. Robotics handle repetitive tasks with unmatched precision, freeing human workers to focus on higher value activities. These innovations not only boost productivity, but also allow factories to respond swiftly to changing market demands. Consumer trends heavily influence the evolution of whipped cream production. With increasing awareness about nutrition and wellness, there is a growing interest in healthier alternatives and transparent labeling. Manufacturers address these concerns by developing innovative formulations and providing detailed information about ingredient origins and production methods. Customization capabilities enable factories to produce niche products catering to regional preferences or emerging dietary fads, such as keto-friendly or gluten-free options. Global trade dynamics also shape the way whipped cream is manufactured. Export markets demand adherence to diverse regulatory frameworks, requiring factories to implement flexible systems capable of meeting varying international standards. Collaboration with suppliers, distributors, and retailers ensures alignment with global supply chains, facilitating timely delivery of products worldwide. Continuous investment in research and development keeps factories at the forefront of technological innovation, ensuring their competitiveness in an ever-evolving marketplace. Beyond the technical aspects of production, the cultural significance of whipped cream cannot be overlooked. In many regions, it is more than just a topping. It is a symbol of indulgence and celebration. From birthday cakes to holiday feasts, whipped cream serves as a versatile ingredient that enhances countless dishes. Its widespread popularity has driven manufacturers to explore new applications and presentations, expanding its appeal beyond traditional boundaries. Factories also prioritize food safety above all else, implementing comprehensive protocols to mitigate risks at every stage of production. Hazard analysis and critical control. Point systems identify potential hazards and establish measures to prevent them. Regular audits and certifications ensure compliance with local and international regulations. Employee training programs emphasize hygiene practices and proper handling procedures, reinforcing a culture of safety throughout the organization. Packaging design plays a vital role in the marketing and distribution of whipped cream. Modern factories invest heavily in developing attractive and functional packaging solutions that appeal to consumers while protecting the product. Innovations in material science have led to the creation of lightweight yet durable containers that reduce shipping costs and environmental impact. Resealable caps and ergonomic handles enhance user convenience, making it easier for customers to enjoy the product without compromising freshness. Supply chain management is another critical component of successful whipped cream production. Efficient logistics ensure a steady flow of raw materials into the factory and finished goods out to retailers. Strategic partnerships with suppliers help secure reliable sources of high-quality cream, while relationships with distributors facilitate rapid delivery to diverse markets. Real-time data analytics enable factories to forecast demand accurately, optimizing inventory levels and reducing waste. Research and development remain central to the growth of the whipped cream industry. Scientists and engineers continuously experiment with new formulations, processing techniques, and packaging technologies to improve product quality and sustainability. Emerging trends in biotechnology and fermentation offer promising avenues for enhancing flavor profiles and extending shelf life. Collaborations with academic institutions and research organizations provide valuable insights into cutting-edge developments that can be applied to commercial production. The economic impact of whipped cream production extends far beyond the factory floor. It supports jobs in agriculture, transportation, retail, and related industries, contributing significantly to local and national economies. By investing in community initiatives and sustainable practices, manufacturers demonstrate their commitment to corporate responsibility and long-term viability. Programs aimed at reducing carbon footprints, conserving water, and promoting biodiversity align with broader societal goals of environmental stewardship. As consumer preferences evolve, so too does the nature of whipped cream production. Health-conscious individuals seek products with fewer additives and artificial ingredients, driving manufacturers to adopt cleaner label approaches. Clear communication about ingredient sourcing and production methods builds trust and fosters loyalty among discerning customers. Educational campaigns highlighting the benefits of whipped cream as part of a balanced diet further reinforce its position as a staple in kitchens worldwide. Finally, the future of whipped cream production promises exciting possibilities. Advances in automation, digitalization, and artificial intelligence will likely transform traditional manufacturing processes, enabling greater efficiency and flexibility. Personalized nutrition platforms may one day allow consumers to customize their own whipped cream blends based on individual dietary needs and preferences. Meanwhile, ongoing efforts to reduce environmental impact and promote social responsibility will ensure that whipped cream remains a beloved and sustainable choice for generations to come. Through precise control of every stage, from cream procurement to final packaging, factories ensure that each container of whipped cream delivers consistent quality and satisfaction. This exploration reveals the depth and complexity behind the seemingly straightforward process of making whipped cream, highlighting the dedication and expertise required to bring this indispensable product to tables everywhere. Golden oil, commonly used in cooking and food production. This journey begins with the careful selection and preparation of sunflower seeds, ensuring that only the highest quality seeds are processed to produce premium oil. Upon arrival at the processing plant, sunflower seeds are subjected to a rigorous cleaning regimen designed to remove a variety of impurities that may have been introduced during harvesting and transportation. This initial phase is critical, as foreign materials such as soil, stones, plant debris, and metal fragments can compromise the efficiency of the extraction process and the quality of the final product. The cleaning process typically involves several stages, each employing specialized equipment tailored to eliminate specific types of contaminants. The first line of defense in the cleaning operation is the magnetic separator. This device utilizes powerful magnets to attract and remove ferrous metal particles from the stream of sunflower seeds. Metal contaminants can originate from various sources, including harvesting equipment and transport containers, and their removal is essential to prevent damage to downstream processing machinery and to ensure product safety. The seeds pass over or through magnetic plates or drums, where metallic impurities are captured and separated from the bulk material. Following magnetic separation, the seeds proceed to vibrating sieves or screens. These machines consist of perforated plates or mesh screens that oscillate at high frequencies, effectively sorting the seeds based on size and shape. Larger impurities, such as sticks, leaves, and oversized debris, are unable to pass through the screen openings and are thus separated from the smaller, uniform sunflower seeds. The vibration intensity and screen aperture sizes are carefully calibrated to optimize the removal of unwanted materials while minimizing the loss of viable seeds. To address the presence of denser contaminants like stones and clumps of soil, the cleaned seeds are then routed through destoners. Destoners operate on the principle of density separation, utilizing airflow and vibration to differentiate between heavier impurities and the lighter sunflower seeds. As the mixture is fed onto an inclined vibrating deck, air is blown through the material from below. The heavier stones resist the upward airflow and migrate to the higher end of the deck, where they are discharged, while the lighter seeds are carried by the vibration to the lower end for collection. This process effectively ensures that only clean seeds advance to the next stage of processing. After the comprehensive cleaning process, the sunflower seeds are ready for dehulling, also known as shelling. Sunflower seeds are encased in hard outer shells or hulls that constitute a significant portion of the seed's total weight. These hulls are low in oil content and can impede the extraction process if not removed. Therefore, dehulling is a crucial step aimed at increasing the efficiency of oil extraction and improving the quality of the resulting oil. The dehulling process begins with the conditioning of the seeds to facilitate the separation of the hulls from the kernels. Conditioning typically involves adjusting the moisture content of the seeds through controlled heating or humidification. Properly conditioned seeds have hulls that are more brittle and easier to crack, enhancing the effectiveness of the dehulling equipment. Once conditioned, the seeds are fed into dehulling machines, which employ mechanical forces to crack the hulls. One common type of dehuller is the centrifugal sheller, which uses a rotating impeller to hurl the seeds against a hard surface, causing the hulls to fracture upon impact. Another method involves the use of roller mills, where seeds pass between counter-rotating rollers that exert compressive and shear forces, breaking the hulls without damaging the kernels. The choice of dehulling equipment depends on factors such as seed variety, desired throughput, and specific plant configurations. Following the cracking of the hulls, the mixture of kernels and shell fragments undergoes a separation process to isolate the oil-rich kernels. This separation is typically achieved through a combination of aspiration and screening techniques. Aspiration involves the use of air streams to lift and remove the lighter hull fragments from the heavier kernels. The mixture is fed into an aspirator, where a controlled airflow lifts the less dense hulls away from the denser kernels, effectively segregating the two components. Screening may also be employed, utilizing vibrating screens with specific mesh sizes to further refine the separation based on particle size and shape. The efficiency of the dehulling and separation processes is paramount, as incomplete removal of hulls can lead to increased fiber content in the oil, affecting its clarity and stability. Moreover, residual hulls in the meal byproduct can diminish its nutritional value and marketability as animal feed. Therefore, processors often implement multiple passes through dehulling and separation equipment to achieve optimal results. balancing the trade-offs between processing time, energy consumption, and product quality. With the sunflower kernels now isolated and free from their hulls, they are ready to undergo further processing to extract the valuable oil contained within. The next stages involve mechanical pressing and/or solvent extraction, each with its own set of procedures and equipment designed to maximize oil yield and quality. These processes will be explored in detail in the subsequent sections, delving into the intricacies of transforming cleaned and dehulled sunflower seeds into the refined oil that reaches consumers worldwide. Now it's time to go into the core phase of sunflower oil manufacturing, the oil extraction process. This is where the golden liquid locked inside the sunflower kernels is separated and collected. The extraction phase typically uses one of two methods, or more commonly, a combination of both, for optimal oil recovery: mechanical pressing and solvent extraction. Each method has its own benefits and limitations, and modern sunflower oil factories are designed to seamlessly integrate these systems into a continuous, high-efficiency process that minimizes waste and maximizes yield. The first step in oil extraction is mechanical pressing, often referred to as expelling. In this process, the dehulled and cleaned sunflower kernels are conveyed into a series of screw presses, also known as oil expellers. These heavy-duty machines consist of a cylindrical barrel housing a rotating helical screw shaft. As the kernels are fed into the expeller from one end, the screw shaft compresses them with increasing pressure as they travel along the barrel. The space between the screw and the barrel gradually narrows, intensifying the pressure and causing the oil to be forced out through small perforations or slits in the barrel wall. This process is incredibly robust and continuous, with some industrial presses capable of handling several tons of seed per hour. However, mechanical pressing alone can only extract about 85% to 90% of the total oil content from sunflower seeds. The remaining 10% to 15% stays trapped in the pressed cake, a solid, fibrous byproduct that still contains a considerable amount of valuable oil. To retrieve this remaining oil and improve overall efficiency, factories employ solvent extraction. Before the solvent extraction phase begins, the pressed cake from the mechanical expeller must be properly prepared. This involves breaking the compacted cake into smaller, uniform pieces using a cake breaker or flaking mill. The flakes are then conveyed to a conditioning unit where they are heated to a specific temperature, usually between 60 to 80 degrees Celsius. This heating not only helps to soften the cell structure of the material, but also enhances the effectiveness of the solvent by improving oil solubility and fluidity. Once conditioned, the sunflower cake is fed into a continuous extractor, typically a horizontal rotary extractor or a loop extractor. In this large stainless steel apparatus, the cake is soaked with a food-grade solvent, most commonly hexane, which has an exceptional ability to dissolve oils. The cake moves slowly through the extractor on a perforated conveyor belt or through a series of baskets, while the solvent is sprayed from above and recirculated from below. As the hexane seeps through the material, it dissolves the residual oil, forming a solution known as micellar. This micellar, containing both oil and solvent, is then pumped out of the extractor and sent to a series of distillation units where the solvent is evaporated and recovered, leaving behind the crude sunflower oil. The evaporation process is conducted under vacuum and controlled heating conditions to ensure complete solvent recovery without degrading the oil. Simultaneously, the now oil-depleted cake, referred to as spent meal, is conveyed to a dissolventizing toaster. This equipment uses steam and indirect heat to remove any residual hexane from the meal, making it safe for use as high-protein animal feed. Next, let's look at the processing of crude sunflower oil, which, at this stage, is a deep amber liquid that contains several impurities, including free fatty acids, phospholipids, pigments, waxes, and trace metals. Though technically oil, This unrefined product is not yet suitable for cooking or bottling. It must be purified and stabilized through a multi-step refining process, which includes degumming, neutralization, bleaching, dewaxing, and deodorization. The first of these refining steps is degumming. In this phase, the crude oil is mixed with a small amount of water or a weak acid, such as citric or phosphoric acid. This causes the naturally occurring phospholipids, also known as gums, to become hydrated and coagulate into a heavier phase that can be separated through centrifugation. The removal of these gums is crucial because they can contribute to off flavors, reduce shelf life, and interfere with further refining stages. The centrifuges used here operate at extremely high speeds, up to 5,000 revolutions per minute, creating centrifugal forces strong enough to separate even microscopic droplets and particles. Once degummed, the oil is subjected to neutralization, where it is treated with a caustic soda solution to remove free fatty acids. These acids can contribute to rancidity and reduce the oil's stability, so their removal is vital for producing a high-quality, shelf-stable product. The soda reacts with the free fatty acids to form soap stock, which is then separated from the oil via another round of centrifugation. The soap stock may be further processed into industrial byproducts such as lubricants or fatty acid distillates, ensuring minimal waste. Now it's time for the bleaching phase. Despite its name, this stage does not involve any chlorine or harsh chemicals. Instead, the oil is mixed with an adsorbent clay material, often activated bleaching earth or acid-activated bentonite, that binds with pigments, trace metals, and other unwanted compounds. The mixture is then heated under vacuum and passed through a filtration system where the spent clay is removed, leaving behind a visibly lighter oil. The objective of this step is not only to improve the color, but also to remove pro-oxidants and residual contaminants that could impact the oil's flavor or stability. But up next is one of the most temperature-sensitive and critical steps: dewaxing. Sunflower oil naturally contains waxes that, while harmless, can cause cloudiness or sedimentation when the oil is refrigerated or stored at low temperatures. To ensure crystal clear oil, particularly for use in transparent bottles, the dewaxing process is implemented. The oil is cooled gradually in a crystallization tank to allow waxes to solidify, and then pass through chilling filters or plate and frame filter presses. The solidified waxes are captured by the filter media and removed, leaving the oil with improved cold stability and clarity. Finally, the last refining step is deodorization. This process removes volatile compounds, including aldehydes and ketones, that can impart undesirable flavors and odors to the oil. Deodorization is carried out in a high vacuum, high temperature distillation column where the oil is subjected to steam distillation at temperatures between 180 to 240 degrees Celsius. The high temperature causes the volatile substances to evaporate, and the vacuum ensures they are swiftly removed from the system. Modern deodorization systems include structured packing and multiple stripping trays that allow for efficient steam-oil contact with minimal thermal degradation of the oil. The end product of this exhaustive refining sequence is a brilliant, light yellow, odorless oil with a neutral flavor and excellent oxidative stability, qualities that make it ideal for cooking, frying, baking, and use in processed foods. The refined sunflower oil is now ready for bottling or bulk packaging, depending on its intended application. Whether destined for supermarket shelves or as an ingredient in snack foods, margarine, or ready-to-eat meals, the oil's journey from seed to bottle is far from over. Now it's time to explore the next critical phase in the industrial sunflower oil production process, the packaging and distribution stage. After undergoing extensive cleaning, pressing, solvent extraction, and refining, the sunflower oil is now fully processed, brilliant in clarity, neutral in flavor, and stable for both cooking and long-term storage. But before it can reach consumers or be used by food manufacturers, the oil must pass through highly automated and carefully controlled packaging systems. These systems are designed to maintain product integrity, optimize shelf life, and meet regulatory and commercial requirements for both retail and industrial distribution. Once the refined sunflower oil leaves the deodorizer, it is pumped into large stainless steel holding tanks. These tanks are equipped with inert gas blanketing systems, typically using nitrogen, to prevent oxidative degradation of the oil. Even trace amounts of oxygen can initiate rancidity, so maintaining a low oxygen environment in storage is critical. The tanks are also thermally insulated and often jacketed for temperature control, maintaining the oil at a stable range of around 25 to 30 degrees Celsius. This ensures that the oil remains fluid and clear, preventing cloudiness that could otherwise form during cooler storage conditions. From these storage tanks, the oil is directed via stainless steel pipelines to the packaging area. The transfer lines are equipped with positive displacement pumps and high sensitivity flow meters to ensure precise, consistent delivery volumes. Before entering the filling systems, the oil passes through final filtration units, often made up of multi-layer stainless steel mesh or polymer filter cartridges to capture any microscopic particulates that may have entered during tank storage. This guarantees that only the cleanest, crystal clear oil reaches the packaging stage. The packaging line is often separated into two main tracks. One for retail-sized bottles, typically ranging from 500 milliliters to 5 liters, and another for bulk containers, such as 20-liter jerry cans, 200-liter drums, or 1,000-liter intermediate bulk containers for industrial clients. The retail packaging line begins with empty bottles being loaded onto a conveyor, either manually or through robotic depalletizers. These bottles are usually made from food-grade PET and are blow molded on-site or sourced from specialized suppliers. Before filling, every bottle passes through a bottle rinser, where a jet of filtered, compressed air or ozonated water is sprayed inside to remove any dust or particles. This ensures microbiological and particulate cleanliness before the oil is introduced. The cleaned bottles are then transferred to multi-head volumetric or gravimetric filling machines. These high-speed machines, capable of filling up to several hundred bottles per minute, are calibrated to extreme accuracy, ensuring every bottle contains the precise labeled volume, no more, no less. The filled bottles are immediately capped by rotary capping machines, which place and tighten tamper-evident screw caps or snap-fit closures. Some systems integrate induction sealing, where a foil liner inside the cap is sealed to the bottle mouth using electromagnetic energy. This creates an airtight, tamper-proof barrier that preserves freshness and prevents leakage during transit. After capping, bottles pass through labelers that apply pressure-sensitive or shrink-sleeve labels. These labels are printed with brand information, nutritional facts, batch codes, and expiration dates using high-speed inkjet or laser coders, allowing for complete traceability of every unit. Following labeling, bottles proceed through automated inspection systems equipped with cameras and sensors that verify fill levels, cap integrity, label alignment, and code legibility. Any non-compliant bottles are automatically rejected via pneumatic arms into separate bins for rework. Approved bottles continue along the line to automated cartoning and case packing stations, where robotic arms place them into cardboard cartons, followed by case sealing with hot melt glue or tape. For bulk packaging, a separate line handles large volume containers. These containers are positioned under filling nozzles that are often suspended from load cells to ensure accurate weight-based filling. Bulk fillers must also incorporate anti-foaming and venting mechanisms to prevent air entrapment, especially at high flow rates. Once filled, containers are sealed with heavy-duty caps or tamper-evident seals and palletized for shipping. All packaging configurations, whether for retail or industrial use, are assigned unique identifiers linked to the master production batch and logged in the plant's ERP system. Now it's time to delve into the logistics and distribution chain, which plays an equally crucial role in maintaining the sunflower oil's quality and ensuring timely delivery to global markets. Once the packaged oil is palletized, it is moved via autonomous guided vehicles or forklifts to climate-controlled storage warehouses. These warehouses are designed for high throughput and efficient inventory turnover. Pallets are organized using barcoded location systems, and warehouse management software ensures that the oldest batches are shipped out first, following the FIFO principle. Transportation from the factory to distribution centers, wholesalers, retailers, or export terminals is typically conducted in temperature-regulated trucks or intermodal containers. For export shipments, ISO tank containers or food-grade flexi tanks are used to transport sunflower oil in bulk volumes over long distances, often across continents. These tanks are insulated and equipped with inert gas blanketing systems to maintain oil stability during the journey. For local or regional deliveries, finished product pallets are shrink-wrapped, strapped, and loaded into trucks equipped with GPS tracking and real-time temperature monitoring. Each shipment includes digital delivery documents with QR codes or RFID tags that sync with customer inventory systems, facilitating seamless unloading and tracking upon arrival. Delivery confirmation, quality checks, and real-time feedback mechanisms are used to verify that every order arrives in optimal condition, both physically and chemically. But up next is one of the most critical dimensions of the modern sunflower oil industry: quality assurance and regulatory compliance. The food-grade nature of edible oil necessitates adherence to stringent quality standards at every stage of the process, from seed selection to final bottling. Every batch of sunflower oil is subjected to a comprehensive suite of analytical tests conducted in on-site laboratories or accredited third-party labs. These tests include parameters like free fatty acid levels, peroxide value, anisidine value, color, moisture content, and soap residue, all of which provide a comprehensive snapshot of oil quality and stability. Gas chromatography is used to profile fatty acid composition, ensuring the oil meets the standard range for linoleic and oleic acid contents. Spectrophotometers analyze color and clarity, while Carl Fisher titration determines residual moisture. These tests not only guarantee regulatory compliance with international standards like Codex Alimentarius, the European Union Food Safety Directives, and the US FDA guidelines, but also help refine internal production protocols. If any parameter falls outside the accepted range, the affected batch is isolated and either reprocessed or discarded. Up next, we focus on one of the more overlooked, yet incredibly vital components of sunflower oil production: byproduct utilization and factory process integration. Modern industrial sunflower oil facilities are designed not only to produce refined oil efficiently, but also to capitalize on every possible output from the sunflower seed itself. This means that even materials which, in earlier generations of oil production, may have been considered waste, are now valuable raw materials for secondary industries or reprocessed within the factory. One of the most important of these byproducts is the sunflower meal or cake that remains after the oil has been extracted. This dense, protein-rich substance is collected immediately following the dissolventizing process and cooled using air blast or counterflow cooling systems to bring the temperature down from over 100 degrees Celsius to ambient levels. This temperature drop is necessary to preserve protein quality and prevent mold growth during storage. The cooled meal is then ground into a uniform particle size using hammer mills or roller mills and passed through vibrating screens to remove any oversized clumps. Sunflower meal is widely used in the livestock and poultry industries as a valuable feed ingredient due to its high protein content and favorable amino acid profile. Factories that produce sunflower oil at scale often have integrated bagging or bulk loading systems for the meal, allowing it to be packaged into 25 or 50 kilogram bags or loaded into bulk silos for shipment in trucks and rail cars. Some facilities even have in-house pelletizing systems that compress the meal into pellets, which are easier to handle, store, and transport. Another byproduct generated during processing is the husk or hull removed during the dehulling stage. These hulls, although devoid of oil and low in protein, have significant value as a biomass fuel. Many sunflower oil factories have transitioned to using these hulls as a renewable energy source to generate heat or steam for use in the facility. The hulls are fed into biomass boilers equipped with particulate filters and emissions control systems where they are combusted cleanly and efficiently. The steam produced powers heat exchangers for oil refining processes like bleaching, deodorization, and dewaxing, reducing reliance on fossil fuels and lowering the factory's carbon footprint. In more advanced facilities, excess steam from the coal-fired boilers is also used to drive small steam turbines, generating on-site electricity that supports lighting, automation systems, and auxiliary equipment. This form of cogeneration enhances energy efficiency and contributes to the plant's sustainability targets. Some operations even sell surplus energy back to the local grid, turning what was once a waste product into a revenue stream. Water recycling is another critical area of integration. Given the extensive use of water in processes such as conditioning, steam generation, equipment washing, and degumming, a closed-loop water treatment system is essential. Wastewater from the plant is collected in large settling tanks, where solids are removed via sedimentation. The water then passes through biological treatment units and membrane filtration systems, such as reverse osmosis or ultrafiltration, to remove organic matter, oil residues, and chemical impurities. The treated water is reused in non-critical applications like boiler feed or equipment cleaning, drastically reducing freshwater consumption. Now turning to process automation, modern sunflower oil facilities operate as highly digitized environments where real-time data governs every aspect of production. Centralized control rooms equipped with HMI panels and SCADA systems provide operators with full visibility and control over temperature, pressure, flow rate, and other parameters at each processing step. Every sensor in the system, from tank-level monitors to flow meters and load cells, is networked to a control system that not only logs data for traceability, but also actively regulates inputs to maintain optimal efficiency. For example, if a temperature deviation is detected in a deodorization column, the SCADA system can automatically adjust the steam valve opening percentage to correct the temperature within seconds. Similarly, in the filling line, digital vision systems detect the fill level and reject any bottles that fall outside preset tolerances. This integration between mechanical systems and digital controls ensures the factory runs continuously with minimal human intervention, reducing errors and improving consistency. Predictive maintenance is another application of advanced automation in sunflower oil production. Vibration sensors, thermographic cameras, and acoustic monitors are placed on motors, gearboxes, pumps, and bearings to detect wear patterns long before failure occurs. The data is fed into AI-driven platforms that analyze trends and forecast the optimal time for maintenance. This prevents unplanned downtime, increases equipment lifespan, and maintains uninterrupted production flow. Inventory management and logistics are similarly digitized. Raw materials, finished oil, packaging supplies, and maintenance components are tracked using barcodes or RFID tags that interface with the plant's ERP system. This allows real-time monitoring of stock levels, automatic reordering when thresholds are reached, and optimized production scheduling based on available resources and demand forecasts. Finished goods are tracked through the entire supply chain, and shipping documents are generated automatically, reducing paperwork and human error. Did you know getting bananas from farms to supermarkets is a massive industrial operation on a scale few ever get to see? Every day, millions of bananas are harvested and packaged with incredible precision before being shipped worldwide. In this documentary, we take you inside the high-tech facilities that handle this global fruit supply, revealing the cutting-edge processes that keep bananas ripe and ready for shelves. Bananas begin their journey in the tropical plantations, where they are carefully cultivated to meet the demands of the global market. The process starts with the selection of optimal banana varieties, with Cavendish bananas being the most widely produced due to their durability and resistance to transportation stress. The banana plants, which are technically large herbs rather than trees, are cultivated in nutrient-rich soil under warm and humid conditions. Farmers carefully monitor the growth of banana plants, ensuring that they receive the right amount of water, nutrients, and protection from pests and diseases. Once the bananas reach the correct stage of maturity, typically around 9 months after planting, the harvesting process begins. Workers use sharp machetes or mechanical cutting tools to carefully cut the large banana bunches, which can weigh up to 50 kilograms. These bunches are placed onto conveyor systems or carried manually to avoid damage. Harvested bananas are quickly transported to centralized collection points, where they undergo a thorough sorting and initial quality inspection. Workers remove any damaged or overly ripe bananas, ensuring only the best quality fruit continues through the production process. The bananas are then washed in large water tanks, often infused with disinfectants to remove dirt, sap, and potential contaminants. This washing step also helps prevent the spread of diseases and fungi that could compromise the fruit's shelf life. Once cleaned, the bananas move onto grading stations, where they are categorized based on size, shape, and external appearance. Factory production standards dictate that only bananas meeting strict criteria proceed to the next stage. At this point, the bananas are separated from the large bunches into smaller clusters, typically consisting of 4 to 7 bananas. These clusters are cut with precision to maintain a uniform presentation. Automated machines or skilled workers carefully trim excess stems to the appropriate length, preventing damage during transportation and further processing. After trimming, the bananas are once again rinsed and placed onto conveyor belts, leading to the next stage of processing. Temperature control is crucial throughout the handling of bananas. To slow down ripening and ensure the fruit remains in peak condition, the bananas are placed in large cooling rooms set to around 13 to 15 degrees Celsius. These controlled conditions help preserve the bananas during transportation to industrial processing facilities, where they undergo further treatment, packaging, and preparation for global distribution. Bananas are highly perishable, so every step of the journey is carefully managed to maximize freshness. Once the bananas arrive at a dedicated processing facility, they undergo another round of inspections. Workers and automated sorting systems check for any defects that may have developed during transportation. The bananas are then placed into climate-controlled storage areas, ensuring that they do not ripen too quickly before packaging. Some bananas are destined for direct sale, while others will be processed into banana-based products such as dried bananas, banana puree, or banana chips. Each of these processing paths requires different equipment and techniques to achieve the desired final product. For fresh banana packaging, the fruit is arranged in trays or cartons designed to protect them from bruising. Packing lines employ automated machinery that gently places the bananas into their designated packaging, ensuring consistent weight and size in each package. Special padded trays or foam inserts are often used to cushion the bananas and minimize damage. The packaged bananas are then labeled, with stickers applied either manually or by automated applicators. Often include barcodes, brand names, and country of origin details. To extend shelf life and prevent premature ripening, some banana shipments are treated with ethylene inhibitors. These substances help slow down the natural production of ethylene gas, which is responsible for the ripening process. In cases where bananas need to ripen on demand, specialized ripening chambers are used at distribution centers. These chambers allow controlled exposure to ethylene gas, ensuring the bananas reach optimal ripeness just before being sent to retail stores. For bananas that will be further processed into products like banana chips, the production process involves additional steps such as peeling, slicing, and dehydration. High-speed peeling machines are used to remove the thick banana skins efficiently. The peeled bananas are then transported via conveyor belts to slicing machines, which cut them into uniform pieces based on the desired end product. These slices are then either fried in hot oil to create banana chips or placed in large dehydration ovens to produce dried banana snacks. The production of banana puree involves an entirely different set of machinery and techniques. After peeling, the bananas are mashed using industrial pulping machines, which break down the fruit into a smooth consistency. The puree is then passed through filtration systems to remove any fibrous material or unwanted particles. Depending on the intended use, the banana puree may undergo pasteurization, a heating process designed to kill bacteria and extend shelf life. The final product is then packaged in large containers or smaller, retail-friendly pouches. Throughout every stage of banana processing, quality control measures are strictly enforced. Automated sensors and human inspectors check for consistency in size, shape, color, and taste. Any defective or subpar bananas are removed from the production line and either repurposed for animal feed, compost, or other secondary uses. Ensuring food safety is paramount, and factories adhere to strict sanitation protocols to prevent contamination. Conveyor belts, slicing machines, and packaging stations are regularly cleaned and maintained to uphold hygiene standards. Once the bananas or banana-based products are ready for distribution, they are carefully loaded onto climate-controlled trucks or shipping containers. These vehicles maintain a state of premature ripening or spoilage. The journey from processing facilities to retailers involves careful logistical planning, ensuring that consumers receive fresh, high-quality bananas at the right stage of ripeness. In cases where bananas are shipped internationally, advanced tracking systems monitor temperature conditions throughout transit, guaranteeing optimal quality upon arrival. Bananas destined for large-scale retail distribution often undergo one final quality check upon arrival at regional distribution centers. Here, ripening specialists assess the fruit's condition and determine whether ethylene gas exposure is necessary to accelerate the ripening process before shipment to supermarkets. Once the bananas reach grocery stores, they are displayed in carefully arranged sections to attract customers while minimizing handling damage. As the bananas move through the processing facility, their journey continues with additional quality control measures. Every banana that passes through the system is subject to strict oversight to ensure it meets the standards set by global markets. Some bananas are set aside for immediate export, while others are prepared for processing into various banana-based products. Each batch is tracked using barcodes or digital systems to maintain traceability, allowing factories to monitor their origins and ensure compliance with regulatory requirements. Bananas that are destined for further processing must first undergo additional cleaning. Large industrial washers use gentle streams of water combined with food-safe sanitizers to remove any remaining residues from the outer peel. For bananas that will be processed into products requiring peeled fruit, high-efficiency peeling machines are employed. These machines operate with incredible precision, using rotating blades and suction systems to remove the thick banana skin without damaging the soft fruit inside. The peeled bananas are then conveyed along sanitized belts toward the next stage of production. For bananas intended for drying, the peeled fruit is sliced into uniform pieces using high-speed industrial slicers. These slices can be adjusted to produce different thicknesses depending on the desired final texture of the dried product. Once sliced, the banana pieces are spread out evenly on large drying trays or conveyor belts, ready to enter specialized dehydration chambers. The drying process typically involves controlled exposure to warm air, which removes moisture while preserving the fruit's natural sweetness. The temperature and humidity levels are carefully monitored to ensure the bananas do not become too brittle or lose their natural flavor. Depending on the facility, some manufacturers may opt for freeze-drying techniques, which use a vacuum process to extract moisture while retaining the fruit's structure and nutrients. Banana chips, a popular snack food, require a different production approach. Instead of dehydration, the sliced bananas are deep-fried in vegetable oil at high temperatures. Large industrial fryers are used to ensure an even cooking process. The frying time is precisely calibrated to achieve a crisp texture without overcooking or burning the banana slices. Some manufacturers enhance the chips by seasoning them with salt, sugar, or other flavorings before they are packaged. Excess oil is removed using centrifugal draining machines, which spin the banana chips to ensure a light and crispy texture. Banana puree production follows another distinct processing pathway. After peeling, the bananas are mashed in large industrial pulping machines. These machines use rotating blades or rollers to break down the fruit into a smooth, consistent mixture. To prevent oxidation and maintain the puree's natural yellow color, antioxidants such as ascorbic acid are often added during this stage. The banana puree is then subjected to pasteurization, where it is heated to a controlled temperature to kill any harmful microorganisms while preserving its nutritional content. Pasteurization is critical for extending the shelf life of banana puree, making it suitable for use in baby food, smoothies, and baking applications. Once the puree has been properly treated, it is packaged in large industrial containers, aseptic pouches, or smaller retail-friendly jars, ready for distribution. Every stage of banana processing requires stringent hygiene controls. Factories implement rigorous sanitation protocols, ensuring that all equipment, conveyor belts, and processing surfaces are regularly cleaned and sterilized. Workers involved in banana handling follow strict hygiene guidelines, wearing protective gloves, hairnets, and sanitized uniforms to prevent contamination. Automated monitoring systems continuously track environmental conditions, ensuring that temperature, humidity, and air quality remain within optimal ranges. Once processed, bananas and banana-derived products are carefully packed to prevent damage and preserve freshness. For fresh bananas, packing stations use automated sorting machines that place the fruit into protective cartons, ensuring uniform weight and size distribution. Banana chips are packaged using nitrogen-flushed bags to prevent oxidation and maintain crispness. Dried bananas and banana puree are sealed in airtight containers, minimizing exposure to moisture and contaminants. Packaging materials are chosen for their durability, ensuring that products remain intact throughout transportation and storage. After packaging, the bananas are prepared for distribution. Fresh bananas are loaded into climate-controlled shipping containers that maintain a stable temperature between 13 and 15 degrees Celsius, preventing premature ripening. These containers are equipped with ventilation systems that regulate air composition, ensuring optimal freshness upon arrival at their destination. Processed banana products follow a different logistics chain, with dried bananas, chips, and puree being transported in standard freight containers under controlled storage conditions. Ripening facilities play a crucial role in the banana supply chain. Upon arrival at distribution centers, fresh bananas may be placed into specialized ripening rooms, where controlled amounts of ethylene gas are introduced. Ethylene is a natural plant hormone that triggers the ripening process, allowing bananas to develop their characteristic yellow color and sweet flavor. Ripening rooms are carefully monitored, with temperature and humidity levels adjusted to ensure uniform ripening without over-ripening or spoilage. Once the bananas reach the desired ripeness, they are shipped to supermarkets, where they are displayed for consumers. In modern banana factories, automation is increasingly integrated into the production process. Advanced robotic systems handle delicate fruit with precision, minimizing bruising and maximizing efficiency. Optical sensors analyze banana quality, sorting them based on color, size, and ripeness. Conveyor belt systems are equipped with real-time monitoring technology, allowing factory managers to track production rates and detect potential issues before they impact output. The integration of data analytics and machine learning further enhances production efficiency, optimizing banana processing workflows based on demand trends and supply chain logistics. Sustainability is also a growing focus in banana manufacturing. Many factories implement eco-friendly initiatives to reduce waste and energy consumption. Banana peels and rejected fruit are repurposed as organic compost, animal feed, or biofuel. Some facilities incorporate solar panels and energy-efficient machinery to lower their carbon footprint. Water recycling systems help minimize water usage, ensuring that banana processing remains environmentally responsible. Efforts to improve fair trade practices and support banana farmers have also gained traction, ensuring ethical and sustainable sourcing of raw materials. Banana production is a complex and highly coordinated process that involves multiple stages of handling, processing, and distribution. From the moment bananas are harvested on plantations to the point where they reach consumers as fresh fruit or processed products, every step is meticulously managed to maintain quality, safety, and efficiency. Advances in technology continue to refine banana processing methods, making it possible to deliver high-quality bananas and banana-based products to markets worldwide. As the banana industry evolves, manufacturers continue refining their processes to improve efficiency, reduce waste, and maximize product quality. The journey from banana plantations to industrial processing facilities is a highly orchestrated operation involving both traditional agricultural techniques and cutting-edge automation technologies. At every stage, from harvesting to packaging, strict protocols are followed to ensure that only the highest quality bananas make it to market. Once bananas have been harvested and sorted, those destined for industrial processing are transported in specialized containers to prevent damage. The journey from the plantation to the factory is carefully managed, with transportation schedules optimized to reduce delays and prevent premature ripening. Bananas that arrive at the factory in a raw state are first subjected to an additional round of inspections. Quality control teams examine each shipment, ensuring that the fruit meets the necessary criteria before it proceeds to the next stage. Upon arrival at the processing facility, bananas undergo a pre-treatment phase. This begins with a thorough cleaning process, where the fruit is washed in large, food-grade water baths. These washing stations are equipped with high-powered jets that remove any residual dirt, pesticides, or surface contaminants. Some factories add mild disinfectants or organic sanitizing agents to the water to eliminate bacteria and fungi that could affect the final product's shelf life. Once washed, the bananas are conveyed to sorting lines, where automated systems use sensors to categorize them based on size, ripeness, and surface quality. For fresh banana packaging, the bananas that meet industry standards are arranged into clusters and gently placed into protective cartons. Advanced robotic arms are sometimes used to handle the fruit, ensuring minimal human contact and reducing the risk of bruising. Packaging lines use precision weighing systems to guarantee uniformity in product distribution. Some packaging facilities use modified atmosphere packaging, where the oxygen levels inside the packaging are carefully controlled to slow down the ripening process. Bananas that are set aside for further processing move to dedicated peeling stations. Peeling bananas on an industrial scale requires specialized machinery that can efficiently remove the thick outer skin while preserving the soft interior. High-speed mechanical peelers use a combination of cutting blades and suction mechanisms to remove the peel in a single motion. For certain banana-based products, additional peeling techniques are employed, such as steam-assisted peeling, where a rapid blast of steam loosens the peel, before mechanical separation. Once peeled, the bananas are inspected again to remove any that are overly bruised or damaged. The peeled bananas are then directed to their respective processing lines based on the final product they will be used for. Bananas designated for puree production are immediately transported to industrial mashing machines, where they are blended into a smooth consistency. These machines operate at high speeds, using rotating blades or pressure systems to break down the fruit into a fine pulp. To maintain the puree's natural color and prevent oxidation, citric acid or ascorbic acid may be added. The puree is then filtered to remove any fibrous material or unwanted solids, ensuring a smooth and consistent texture. Bananas intended for drying are sliced using automated slicing machines that produce even, uniform pieces. These banana slices are then placed onto mesh conveyor belts, which carry them through drying tunnels. The drying process varies depending on the manufacturer, but it typically involves controlled exposure to warm air at temperatures between 50 and 70 degrees Celsius. This gradual dehydration process removes moisture while preserving the natural sugars in the fruit, resulting in a sweet and chewy texture. Some manufacturers opt for freeze drying, which involves rapidly freezing the banana slices before placing them in a vacuum chamber to remove moisture. This method helps retain more of the banana's original flavor and nutritional content. Banana chips, a widely popular snack, undergo a frying process to achieve their crispy texture. The peeled bananas are first cut into thin slices before being submerged in large vats of hot vegetable oil. The frying process takes only a few minutes, during which the banana slices turn golden brown and develop their characteristic crunch. After frying, excess oil is removed using centrifugal draining machines, which spin the chips at high speeds to eliminate any remaining grease. To enhance flavor, the banana chips may be lightly salted, sweetened with honey, or coated in flavored seasonings before being packaged. Throughout every stage of production, factories implement rigorous quality control measures to ensure food safety and consistency. Optical scanners and high-speed cameras are used to detect imperfections, sorting out any defective bananas or banana products. Workers in food safety laboratories conduct testing, checking for bacteria, yeast, and mold that could compromise product quality. Metal detectors and X-ray machines scan packaged products for any foreign contaminants before they are cleared for distribution. The final stage of banana processing involves packaging and storage. Fresh bananas are packed in ventilated cartons that provide airflow to regulate ripening. Banana chips and dried banana products are sealed in airtight packaging to maintain freshness and prevent moisture absorption. Banana puree is packaged in sterile, food-grade containers, which are often vacuum sealed or heat treated to ensure an extended shelf life. In large-scale food manufacturing, bulk containers of banana puree may be shipped to other processing facilities, where they are used in products such as baby food, smoothies, yogurt, and baked goods. Once packaged, the banana products are stored in climate-controlled warehouses before being transported to retailers and distribution centers. Logistics teams carefully plan shipping routes to minimize transit time and ensure that the products arrive in optimal condition. Fresh bananas are typically shipped in refrigerated trucks or containers, where the temperature is carefully regulated to prevent premature ripening. Ripening centers at distribution hubs monitor the banana's condition, exposing them to controlled amounts of ethylene gas when necessary to trigger the final ripening process before they reach grocery store shelves. Banana factories continuously innovate to improve efficiency and sustainability. Many facilities have adopted eco-friendly initiatives to reduce waste and energy consumption. For instance, banana peels and other byproducts from the production process are repurposed as compost, livestock feed, or biofuel. Some factories incorporate water recycling systems, filtering and reusing water from the washing process to minimize resource consumption. The use of solar energy and other renewable power sources is also becoming more common in banana processing plants, helping to reduce the industry's overall carbon footprint. The integration of smart technology and automation is revolutionizing banana production. Artificial intelligence, AI, and machine learning algorithms are used to optimize sorting, detect defects, and predict supply chain trends. Advanced robotics are being implemented to handle delicate fruit more efficiently, reducing human labor costs while increasing processing speeds. Data analytics tools allow factory production in real time, making adjustments to improve efficiency and reduce waste. The demand for banana-based products continues to grow, driven by consumer preferences for healthy, natural snacks and ingredients. Banana processing plants are expanding their product offerings to include innovative items such as banana flour, banana-based protein bars, and freeze-dried banana snacks. The industry is also focusing on sustainable sourcing, ensuring that bananas are grown using environmentally responsible farming practices that support fair wages and ethical labor conditions for workers. As the banana industry expands, factories are continuously developing new techniques to optimize efficiency, reduce waste, and maintain high product quality. The production cycle is carefully monitored, from the moment bananas are harvested in plantations to their transformation into various consumer products. Each stage is executed with precision to meet global market demands while ensuring sustainability and food safety. Once fresh bananas have been sorted, cleaned, and prepared for processing, the next step depends on their intended use. Some bananas will be packaged for fresh consumption, while others will be transformed into banana puree, dried banana products, or banana-based ingredients used in food manufacturing. For fresh bananas, factories implement protective packaging solutions to prevent bruising and ensure that the fruit remains in excellent condition throughout transportation and storage. These packaging solutions may include cushioned cartons, foam inserts, or breathable plastic wraps that regulate moisture levels and slow down ripening. Fresh bananas are often shipped in refrigerated trucks that maintain a stable temperature of around 13 to 15 degrees Celsius. This temperature range is crucial as it prevents premature ripening while keeping the fruit firm and fresh. Advanced logistics tracking systems monitor temperature fluctuations in real time, ensuring that bananas are transported under optimal conditions. If temperatures rise too high during transit, the bananas may ripen too quickly, leading to shorter shelf life and increased waste. Conversely, if temperatures drop too low, chilling injury can occur, causing the bananas to develop brown or black spots and compromising their quality. For bananas that undergo further processing, the industrial peeling phase is a critical step. While some banana-based products require manual peeling, most large-scale factories use specialized peeling machines to remove the thick banana skins efficiently. These machines operate using rotating blades or suction systems, ensuring that the fruit is peeled quickly and cleanly. In some cases, banana peels are softened using a brief steam treatment before being mechanically separated from the fruit. This method helps reduce waste and increases the yield of usable banana flesh. Once peeled, the bananas must be processed quickly to prevent oxidation, which can cause them to turn brown. For banana puree production, the peeled bananas are immediately transferred to high-speed pulping machines. These machines use rotating metal drums with fine mesh screens to break down the fruit into a smooth, uniform puree. The puree is then passed through filtration systems to remove any unwanted fibers or solid particles. To maintain color and flavor, natural antioxidants such as citric acid or ascorbic acid are added. Some manufacturers also incorporate mild pasteurization, heating the puree to a controlled temperature to eliminate bacteria and extend shelf life without compromising nutritional value. The banana puree is then packaged in aseptic containers, ensuring that it remains free from contamination. In some cases, the puree is concentrated by removing excess water, creating a thicker, more versatile product used in baby food, baked goods, and smoothies. The concentrated puree is typically stored in large industrial drums or vacuum-sealed pouches before being distributed to food manufacturers worldwide. For dried banana production, the peeled fruit is sliced into uniform pieces using precision slicing machines. These machines ensure that each banana slice maintains a consistent thickness, which is essential for even drying. The banana slices are then arranged on conveyor belts or drying racks, ready to enter industrial dehydration chambers. The drying process varies depending on the manufacturer and the intended final product. Traditional air drying methods involve exposing the banana slices to warm, circulating air at temperatures between 50 and 70 degrees Celsius. This gradual drying process removes moisture while preserving the fruit's natural sweetness and texture. Some manufacturers use freeze drying, a technique that involves freezing the banana slices and then placing them in a vacuum chamber. The vacuum removes moisture without subjecting the fruit to heat, resulting in a crisp, lightweight product that retains more of the banana's original nutrients and flavor. For banana chips, the production process is slightly different. Instead of drying, the banana slices are submerged in hot vegetable oil and fried until they develop a crunchy texture. Large industrial fryers maintain a consistent oil temperature, ensuring even cooking and a uniform golden brown color. After frying, excess oil is removed using centrifugal draining machines, which spin the chips at high speeds to extract any remaining grease. Some manufacturers apply additional flavoring, such as salt, sugar, cinnamon, or honey glaze, before packaging the banana chips in airtight bags to preserve freshness. Throughout the processing stages, factories implement strict food safety and quality control measures. Automated sorting systems use high-resolution cameras and optical sensors to inspect banana slices, puree, and chips for consistency in color, size, and texture. Any defective or substandard products are removed from the production line. Metal detectors and X-ray scanners check packaged banana products for potential contaminants, ensuring that every item meets the required safety standards before it reaches consumers. Banana factories also prioritize waste reduction and sustainability. Peels and other organic byproducts from the production process are repurposed in various ways. Some factories use banana peels as livestock feed, while others process them into compost or biofuel. Advanced waste management systems help minimize environmental impact, with some manufacturers investing in water recycling technologies to reduce water consumption during the cleaning and washing stages. As consumer demand for banana-based products grows, factories continue to innovate and expand their offerings. Beyond traditional banana puree, chips, and dried bananas, manufacturers are exploring new product categories, including banana flour, prepackaged banana smoothie blends, and high-protein banana bars. Banana flour, made by grinding dried bananas into a fine powder, is gaining popularity as a gluten-free alternative for baking and cooking. This versatile ingredient is used in everything from bread and pancakes to energy bars and nutritional supplements. Banana processing facilities also invest heavily in automation and smart technology to improve efficiency. AI-powered sorting machines analyze banana quality in real time, adjusting processing parameters to optimize output. Robotic arms are increasingly used for packaging, reducing the need for manual handling and minimizing product damage. Real-time data analytics help factory managers monitor production performance, identify inefficiencies, and implement improvements that enhance productivity and reduce costs. The global banana industry relies on a well-coordinated supply chain to ensure that fresh and processed bananas reach consumers in peak condition. Distribution networks are carefully managed, with warehouses and ripening centers strategically located near major markets. Retailers use advanced inventory management systems to track banana shipments and predict demand, ensuring that stores remain stocked with fresh bananas while minimizing waste. In ripening centers, fresh bananas undergo controlled ethylene exposure to accelerate ripening before they are sent to supermarkets. The timing of this ripening process is critical, as it determines the banana's appearance and texture upon reaching store shelves. Ethylene gas concentrations, temperature, and humidity are carefully regulated to achieve uniform ripening without over-ripening or spoilage. Banana factories continue to evolve, integrating the latest advancements in food technology, sustainability, and logistics. As consumer preferences shift toward healthier and more sustainable food choices, the banana industry is adapting by offering organic, fair trade, and minimally processed banana products. These initiatives ensure that banana production remains both economically viable and environmentally responsible, meeting the needs of a growing global population while reducing the industry's ecological footprint. The meticulous handling of bananas throughout their journey from plantation to processing facility ensures that they maintain their freshness and quality, whether they are destined for fresh consumption or further industrial processing. The seamless transition between these stages requires advanced logistical coordination, as bananas must be transported quickly to prevent over-ripening while maintaining optimal storage conditions. Once inside the processing facility, each banana undergoes a series of treatments tailored to its final intended use. Bananas that are meant for fresh sale are carefully packaged in protective cartons, but the process doesn't end there. These fresh bananas are often stored in climate-controlled warehouses, where specialized ripening chambers help regulate their maturation. Since bananas ripen naturally through the release of ethylene gas, these chambers provide a controlled environment where ethylene exposure is adjusted based on shipment schedules. This process ensures that bananas arrive at supermarkets at the perfect stage of ripeness, ready for consumers to purchase. The ripening rooms are monitored with precision sensors that measure humidity, temperature, and gas concentration, ensuring that no batch over-ripens or becomes too soft before reaching store shelves. Meanwhile, for bananas destined for further processing, their journey involves a more intensive transformation. Once peeled using specialized machinery, these bananas are quickly moved into processing lines to prevent oxidation, which can lead to undesirable browning and flavor changes. Depending on their end use, the bananas are either mashed into puree, sliced for drying, or prepared for frying into banana chips. Banana puree production requires high-speed pulping machines that use stainless steel blades to break down the fruit into a smooth consistency. These machines operate in continuous production lines, with the puree moving through filtration systems that remove any unwanted fibers, seeds, or imperfections. The temperature of the puree is maintained at controlled levels to preserve its natural sweetness and prevent microbial growth. Some manufacturers incorporate flash pasteurization, a brief but effective heat treatment to extend the puree's shelf life without compromising flavor or nutritional value. The final product is then stored in sterilized tanks before being packaged in either small retail pouches or industrial-sized drums for bulk distribution. For dried banana products, the process is slightly different. Once peeled, bananas are fed into high-precision slicing machines that ensure each piece is uniform in size and thickness. The slices are then transferred to conveyor systems that guide them through dehydration chambers, where controlled airflow and heat gradually remove moisture from the fruit. This drying process can take several hours, depending on the desired texture and final moisture content of the product. Some manufacturers use vacuum drying or freeze drying techniques to enhance texture and retain more nutrients. These methods help produce crisp, long-lasting banana snacks that remain shelf-stable for extended periods. In banana chip production, the peeled and sliced bananas are submerged in industrial frying vats filled with hot vegetable oil. These vats operate at precise temperatures to ensure the banana slices fry evenly, developing a golden brown crispiness without burning. After frying, excess oil is removed using high-speed centrifugal drying machines which spin the chips rapidly to eliminate residual grease. Some manufacturers season the chips immediately after frying, using automated sprayers to apply salt, sugar, or various flavor coatings. The finished banana chips are then transported to packaging stations, where they are sealed in airtight bags to preserve their crunch and prevent oxidation. Throughout the entire banana processing workflow, factories implement stringent quality control measures. Automated vision systems equipped with high-resolution cameras inspect banana slices, puree, and chips for consistency in size, color, and texture. Any substandard products are diverted from the main production line and repurposed for secondary uses such as animal feed or composting. Metal detectors and X-ray scanners provide additional safety checks, ensuring that no foreign contaminants are present in the final packaged products. The packaging process itself is highly automated, with conveyor belts guiding products into pre-measured containers. Fresh bananas are placed in breathable cartons that allow for ventilation, while banana chips and dried banana slices are packaged in nitrogen-flushed bags that prevent oxidation and extend shelf life. For banana puree, aseptic packaging methods are used to maintain product freshness without the need for refrigeration. Some large-scale food manufacturers purchase banana puree in bulk containers, which are then integrated into their own production lines for making baby food, desserts, and bakery items. Once packaged, banana products must be stored and distributed efficiently. Climate-controlled warehouses maintain optimal conditions for each type of banana product, ensuring that fresh bananas do not ripen too quickly and that processed banana items remain stable. Logistics teams coordinate shipments using real-time tracking systems, optimizing delivery routes to minimize transportation times and ensure products arrive in peak condition. Fresh bananas are often transported in refrigerated containers that maintain a consistent temperature, preventing premature ripening. These containers are equipped with ventilation controls that regulate humidity and air composition, ensuring that bananas remain firm and resistant to bruising during long-distance transit. Upon arrival at distribution centers, these bananas undergo a final ripening stage, where ethylene exposure is carefully managed to achieve the perfect color and texture before they are shipped to grocery stores. Banana-based products, such as chips, dried bananas, and puree, follow a slightly different distribution model. Since these products have longer shelf lives, they are often stored in dry warehouses before being shipped to retail stores or food manufacturers. These warehouses use advanced inventory management systems to track stock levels and prevent overproduction, ensuring a steady supply chain without excessive waste. The sustainability aspect of banana processing is a growing focus for manufacturers. Many factories have adopted eco-friendly initiatives to reduce their environmental impact. Banana peels and other organic byproducts are repurposed in various ways, such as being converted into animal feed, biofuel, or compost for agricultural use. Some facilities implement water recycling systems to minimize waste in the washing and processing stages, ensuring that water usage remains efficient. Additionally, energy-efficient machinery and solar-powered production plants are becoming more common, helping factories reduce their overall carbon footprint. In recent years, consumer demand for ethically sourced and organic bananas has driven changes in banana processing. More factories are adhering to fair trade standards, ensuring that banana farmers receive fair wages and that environmentally sustainable farming practices are followed. Organic banana production eliminates synthetic pesticides and fertilizers, requiring stricter handling protocols to maintain certification standards. These organic bananas go through the same processing methods, but must be kept separate from conventionally grown bananas throughout the supply chain to maintain their organic status. Technology continues to revolutionize banana processing, with artificial intelligence and automation playing an increasing role. AI-driven quality control systems analyze bananas for defects with greater accuracy than human inspectors, reducing waste and improving overall efficiency. Automated robotic arms handle delicate bananas with precision, ensuring minimal bruising during sorting and packaging. Data analytics software optimizes supply chain logistics, predicting demand patterns and helping factories adjust production schedules to meet market needs. The efficiency of banana processing factories relies on a combination of cutting-edge automation, rigorous quality control, and sustainable practices. From the moment bananas enter the facility to their final packaging and distribution, every step is carefully designed to maximize freshness, preserve nutritional value, and minimize waste. While fresh bananas undergo controlled storage and ripening processes to ensure peak quality upon arrival at retail stores, processed banana products like puree, chips, and dried slices follow more complex manufacturing pathways requiring specialized equipment and techniques. One of the critical elements of banana processing is maintaining the delicate balance between speed and quality. Since bananas are highly perishable, factories must operate with precision to prevent spoilage and ensure that only the highest quality fruit is used. Advanced sorting lines use a combination of human inspection and artificial intelligence-driven sensors to evaluate bananas based on their color, size, firmness, and surface condition. High-resolution cameras scan each banana as it moves along conveyor belts, identifying bruises, blemishes, or irregularities that could affect product quality. Any substandard bananas are automatically diverted to secondary processing lines where they may be repurposed for animal feed, composting, or biofuel production. For fresh banana packaging, factories utilize automated systems that gently place bananas into protective cartons or plastic trays. Each package is weighed to ensure consistency, with advanced robotic arms adjusting the number of bananas per carton if necessary. The packaging materials are designed to provide adequate ventilation while minimizing physical damage during transportation. Some factories also use biodegradable or recyclable packaging solutions, aligning with global sustainability trends and reducing plastic waste in the supply chain. Bananas that undergo further processing are peeled using high-speed peeling machines, which separate the edible fruit from its thick outer skin with remarkable efficiency. The peeled bananas are then subjected to additional cleaning, where they are rinsed in purified water infused with mild food-grade sanitizers to eliminate any remaining contaminants. Once cleaned, the bananas are directed toward their designated production lines based on the final product requirements. Banana puree production requires industrial-scale pulping machines, which operate using rotating blades or pressure-based extraction methods to break down the fruit into a uniform consistency. These machines are engineered to handle large volumes of bananas per hour, ensuring continuous output without interruptions. To prevent the puree from oxidizing and developing an undesirable brown hue, factories introduce natural preservatives such as lemon juice or ascorbic acid. The puree then undergoes pasteurization, a crucial step that involves briefly heating the product to eliminate harmful microorganisms while preserving its fresh taste and nutritional content. After pasteurization, the banana puree is rapidly cooled and transferred into sterilized storage tanks or aseptic packaging containers. For dried banana production, the peeled fruit is carefully sliced into even round or strips using precision cutting machines. The sliced bananas are then arranged on large drying trays or mesh conveyor belts that transport them through industrial dehydration chambers. These chambers use controlled heat and airflow to gradually reduce the moisture content of the bananas while retaining their natural sweetness. The drying time varies based on the desired texture, with chewy, dried bananas requiring slightly higher moisture retention than crispy banana chips. Some manufacturers opt for vacuum drying or freeze drying methods, which help preserve the banana's original structure, flavor, and nutrient profile more effectively than conventional drying techniques. Banana chip production follows a different path, involving deep frying to achieve a crunchy texture. Once sliced, the banana pieces are fed into large capacity frying vats filled with hot vegetable oil. The frying process lasts only a few minutes, during which the natural sugars in the bananas caramelize, enhancing their sweetness and contributing to their golden brown appearance. Once fried, the banana chips are rapidly cooled and transferred to centrifugal drying machines, which remove excess oil and ensure a light, crisp finish. Some manufacturers add flavor enhancements such as cinnamon, honey, or even spicy seasonings before sealing the chips in airtight packaging. Quality control is a non-negotiable aspect of banana processing. Each production batch is subjected to multiple layers of testing, ensuring compliance with food safety regulations and consumer expectations. Optical scanners analyze banana slices and puree for consistency in texture and color, while microbial testing ensures that products remain free from harmful bacteria, yeast, and mold. Factories also employ metal detection and X-ray inspection systems to identify any potential foreign contaminants before the products are packaged and shipped. The packaging stage is highly automated, with conveyor belts guiding banana products into their respective containers. Fresh bananas are packed in ventilated cartons that allow for sufficient airflow, ensuring gradual ripening without over-ripening. Banana puree is sealed in vacuum-packed pouches or bulk-sized aseptic containers, which protect the product from oxidation and contamination. Dried bananas and banana chips are packaged in moisture-proof bags filled with nitrogen gas to prevent oxidation and preserve crispness. Once packaged, banana products are moved to temperature-controlled storage areas before distribution. Fresh bananas are carefully stored in ripening chambers at distribution centers, where ethylene gas exposure is calibrated to trigger controlled ripening before shipment to supermarkets. This process ensures that bananas reach store shelves at the perfect stage of ripeness, allowing consumers to enjoy them at their peak. For banana-based processed products, distribution logistics involve coordination between factories, warehouses, and retailers. Bulk banana puree shipments are often sent to food manufacturers, where they are used as ingredients in smoothies, yogurt, baby food, and baked goods. Dried bananas and banana chips are transported to grocery stores, convenience shops, and online retailers, where they are sold as snacks. Advanced inventory management systems track product movement in real time, ensuring that retailers receive fresh supplies while minimizing storage time. Sustainability initiatives play an increasingly vital role in banana processing. Many factories implement zero-waste policies, where byproducts such as banana peels and unused fruit are repurposed rather than discarded. Some facilities process banana peels into animal feed, organic fertilizers, or even bioplastics. Others convert banana waste into bioethanol, an alternative fuel source that reduces dependence on fossil fuels. Water conservation measures, such as recycling systems that purify and reuse water from the washing process, further contribute to the industry's environmental responsibility. Technology continues to drive innovation in banana processing, with artificial intelligence and automation enhancing efficiency and reducing operational costs. AI-driven quality control systems detect imperfections with greater precision than human inspectors, ensuring that only the best bananas make it to market. Machine learning algorithms analyze production data in real time, identifying trends that allow factories to optimize processing speeds, reduce waste, and improve overall efficiency. Robotics are increasingly integrated into packaging lines, where they handle delicate bananas with minimal risk of damage. As the demand for banana-based products grows, factories are expanding their product lines to cater to evolving consumer preferences. Beyond traditional banana puree, chips, and dried fruit, manufacturers are introducing new items such as banana flour, freeze-dried banana powder, and protein-enriched banana-based snacks. These innovations cater to health-conscious consumers seeking natural, minimally processed foods with high nutritional value. From plantation to processing facility to final distribution, banana production is a seamless operation that combines agricultural expertise, advanced manufacturing techniques, and sustainable practices. The ability to efficiently process and transport bananas on a massive scale ensures that consumers worldwide continue to enjoy this beloved fruit in various forms. Whether eaten fresh, blended into a smoothie, baked into goods, or enjoyed as a crispy snack, bananas remain one of the most versatile and widely consumed fruits globally. Once banana products are processed and packaged, they must be distributed efficiently to reach retailers, food manufacturers, and consumers worldwide. For fresh bananas, the final stage of ripening takes place in specialized ripening centers located near major markets. These centers use advanced ethylene gas chambers to trigger the banana's natural ripening process, ensuring they develop the ideal color, texture, and sweetness before being shipped to grocery stores. Temperature and humidity are carefully controlled during this stage, preventing premature spoilage while allowing for even ripening across each batch. Once the bananas reach their optimal ripeness, they are packed into ventilated boxes and loaded onto temperature-controlled trucks for final distribution. Processed banana products such as banana chips, dried bananas, and banana puree follow a slightly different logistics pathway. Since these products have a longer shelf life than fresh bananas, they are stored in climate-controlled warehouses before being shipped to retailers, wholesalers, and food manufacturers. Advanced inventory tracking systems monitor stock levels in real time, ensuring that shipments are distributed efficiently while minimizing excess inventory and storage costs. Many factories have implemented just-in-time manufacturing strategies, producing banana-based products based on real-time demand forecasts to reduce overproduction and food waste. Banana puree, in particular, is a key ingredient in a wide range of food products, including baby food, yogurts, smoothies, baked goods, and sauces. Bulk shipments of banana puree are transported in large aseptic containers or barrels, which keep the product sterile and fresh without the need for refrigeration. These containers are shipped directly to food manufacturing plants, where the puree is incorporated into various recipes. Some food companies also receive freeze-dried banana powder, which can be easily rehydrated and used in an assortment of food and beverage applications. Dried bananas and banana chips are transported in airtight packaging that preserves their crunch and prevents moisture absorption. Retailers often display these products alongside other dried fruit snacks, appealing to health-conscious consumers looking for natural, convenient snack options. The packaging of banana chips is designed to be lightweight yet durable, ensuring that the chips remain intact during shipping and storage. Many brands use nitrogen flushing to replace oxygen inside the packaging, which helps prevent oxidation and extends shelf life. One of the biggest challenges in banana production is maintaining sustainability and ethical sourcing. Given the vast scale of banana cultivation and processing, the industry has faced increasing scrutiny regarding environmental impact, labor conditions, and fair trade practices. To address these concerns, many banana processing facilities have adopted sustainable sourcing policies, ensuring that bananas are grown using environmentally friendly agricultural methods. These initiatives include reducing pesticide use, conserving water through efficient irrigation techniques, and promoting biodiversity in banana plantations. Fair trade certification has also become a key factor in the banana industry,